We're starting the 2 o'clock session. I'm Thomas Brophy, President of the Institute of Noetic Sciences. I'm chair of this session. And the way we're planning that it will go, we'll have a lot of discussion and feedback, but we've got a rough structure of 20 minutes for each of us 7 presenters, and we can include a little bit of Q&A depending on the presenter if they get done before the 20 minutes, in that 20 minutes for each one. And then we'll have a break after 5 presenters at 3:50 about, and we'll have a brief break. And then we'll have the final 2 presenters, which are Stuart Hameroff and me. Then we should have about an hour of general Q&A and back and forth. And we're starting off with Nassim Haramein. The second one will be our online presenter, Don Hoffman, and we'll go from there.
Thank you. Thank you. So great to be here. I'm excited to present this work. Some of the stuff I'm going to present today hasn't been presented ever and is in peer review right now, so it's very, very fresh. And I made my presentation as light as possible, you know, so that it's not so technical. So it's like a bird's eye view on the technicalities, but I'm happy to discuss the technicalities individually with you guys anytime you want. And I'm printing my paper that's in peer review right now, so I'll have some copies as well if you're interested in the details. But let's just start. So let's start with Einstein and Rosen, 1935. And most people, when you mention this paper that they published, they think right away about wormholes. Because it was a solution to Einstein's field equation, to his general relativity equations, that he was trying to apply to atomic and subatomic particles. And so people don't actually realize that typically. They think of wormholes as these things that are happening in the cosmos somewhere, but when these equations were written by Einstein and Rosen, they were trying to apply it to the proton, the nuclei of the atom. And they were trying to describe atomic structure with general relativity. They were trying to geometrize quantum mechanics. And they were trying to do that because they were trying to get rid of infinities that were, that they were trying to like make more geometric and fundamental in nature instead of having particles and so on. So they tried to apply general relativity to the atomic level, and general relativity solutions are actually wormhole solutions. And so the problem they ran into, it was a great idea, it was beautiful in its conceptual notions, but the problem they ran into is that when they applied the Schwarzschild solution to Einstein field equation to the proton, they got a radius that is 10 to the minus 54 centimeters, and so that's like below the Planck length. It's like so teeny, it's like not possible, and they say, oh, it doesn't work, and eventually that whole approach got abandoned, although wormholes have been part of some of the theoretical work that's going on in astrophysics and so on. So, and nobody noticed, this is remarkable, but nobody noticed, until me it seems, that you could reverse the equation. And if you reverse the equation, that's it, meaning that instead of trying to keep the proton, to keep the mass of the proton and solve for the radius, you change the mass, keep the radius, and see what the mass should be for the little black hole proton. And when you do that, the value you get is the gravitational coupling constant. And if somebody would have done that, it would have turned on the lights, although at that time they didn't have all the pieces they needed to solve it. But later on, certainly, to realize that you get the relationship between the gravitational force and the strong force, the nuclear force, in the ratio of the energy you need to put in the proton to make it a mini black hole. So this is, and it's not an approximation. I want to make sure you understand this is actually exact. It exactly gives the relationship between the strong force or between the color force and the gravitational force. So it's showing that really the strong force is curving space-time, but where is the energy coming to produce that force to make the proton such a thing? So another thing that seems like nobody has noticed is that this alpha G, right, this gravitational coupling constant, you all following what I'm saying? Yeah, you're all with me? Okay, that this ratio between the strong force and the gravitational force, which is between the proton and, the far from the proton, the gravitational field, is as well the same ratio between the proton and the Planck force, which is the density of the quantum vacuum at the Planck scale, at the very small scale of the fluctuation of the electromagnetic field. These fluctuations of the electromagnetic fields are not coming from some garage inventor. They actually at the basis of quantum mechanics. It was as a result of the discovery of Max Planck trying to work out the black body radiation that eventually he found that at 0 Kelvin, a harmonic oscillator still has energy, and he called it zero-point energy. And the relationship between that energy, which is fundamental to quantum mechanics, and the color force is alpha G. And so you have this relationship. So let's put it in the correct order. So now you have the Planck force, you apply alpha G, that ratio, right? Showing it's not just a ratio between the strong force or the color force and the gravitational force, it's a fundamental scaling ratio. So you have this energy that's fluctuating everywhere in the space, the zero-point energy, one screening or one reduction of alpha G, and you get the color force, another one, and you get the residual strong force, or you get the gravitational force far from the proton. So that cannot be a coincidence. This is exactly what Einstein was trying to do. He just didn't realize that he had to account for the quantum vacuum fluctuation inside the proton that was providing the energy to produce the strong force. And so if you apply that, there's complexity, and I'm making big jumps, and I understand, just like come along with me. I'll give you the details in the paper, but there's a direct relationship to mass. So then again, you start with quantum vacuum fluctuation, and you find that the black hole mass, right, the energy necessary for the color force occurs and after an alpha G, and after another alpha G, you get the rest mass of the proton. And so you're going from the rest mass of the proton with square root of alpha g multiplied by the Planck mass, and you get the rest mass of the proton. And I want to insist that all these relationships are exact. I'm not like just the exact with as many digits of accuracy that we have from experiments. And so it's very critical as well to see that like you have these relationships, both of the mass and the forces emerging from zero-point energy, emerging from electromagnetic quantum vacuum fluctuation, from this fundamental field at the base of creation that is producing the forces and the masses we observe in our everyday reality. And you know, there's many implications to what I just showed you, many, which includes, you know, cosmology, black hole physics, Hawking radiation, and we're going to see some of that. But this is the paper that's in peer review right now. So we released the first version of this paper almost 2 years ago, and we have now solve some of the equation in a more deeper way. So we have a second edition of the paper in peer review right now. And in this one, we solve for the Klein-Gordon equations and eventually for Einstein field equation. So we solve all the metrical space to show that these forces emerge naturally from quantum vacuum fluctuation. So if you have a little black hole in the center of the atom, in the center of the nuclei of the atom, in the center of a proton, because the energy necessary to produce the color force is exactly the energy required to make that thing a little proton, then that a little black hole proton, that black hole proton will radiate energy, right, in terms of Hawking radiation, because black holes radiate energy in terms of Hawking radiation. So we calculated this. Rho vac here is the density of the vacuum, and it's being screened, right? Like the Hawking radiation is the entropy of the surface radiating energy due to vacuum fluctuations. And when you make the calculation, sure enough, I'm sorry, I'm trying, oops, a little too fast. Okay, so you get the correct mass for the proton. So as the radiation occurs, so you output the temperature, and then you get the energy of the radiation of the little black hole, and you get the exact rest mass of the proton. So we are experiencing the radiation of the mini proton black hole and measuring the rest mass of the proton. I know this can be shocking, but I just want to say I'm just completing what Einstein had started, okay? Not my idea to make the little proton a black hole, though I came up with it as well independently, but then I realized he had beat me by a few decades, all right? And it actually gives the correct answer, and then a black hole that radiates will lose energy. So you can calculate the evaporation of such a little black hole. And when you consider the energy that's provided by quantum vacuum fluctuations inside the proton, then the stability of the proton is extraordinary, 10 to the 44th years. Okay, just to give you an idea, that's the age of the universe, and this is 10 to the 44th years, right? So it's quite stable. Never mind that when you do the correlation function equations, which describe what's going on inside the proton with the vacuum fluctuation, you find the rest mass as well inside the proton. So actually the vacuum fluctuation are providing the energy for the rest mass, which it's radiating, so it's stable probably to infinity, and so on. And so it has like feedback dynamics, right, between the vacuum inside and the vacuum outside. There's a continuous feedback dynamic, and that we solved in Einstein field equation to try to figure out because what I showed you originally is just the force at that point, the force at that point. Here I'm solving space-time to get the curve of the force, the dynamic of the force. And when you do that, you find that the force obeys the Yukawa potential. You see, from the Planck force at the very top there, okay, all the way down to the color force, it's so steep, the drop in energy across the boundary of the proton that it produced a Yukawa potential. It's so steep that we had to zoom in to see the potential change. And then after that, it becomes the residual strong force, and then the Newtonian force, or the gravitational force. So we unified the Planck force with the color force, the residual strong force, and gravity, all coming out of quantum vacuum fluctuations. And I want to say again, these values are exact, okay? And some of these values are measured. For instance, the pressure of the strong force was just measured a few months ago. We nailed it, okay? It's about the pressure internal to a neutron star. It's very, very high, right? And then the residual strong force, we nailed that, and the gravitational force. So we get all the correct answer, and now we have a scaling understanding on how quantum vacuum fluctuation decoheres as you scale and becomes weaker and weaker. And that's why we think that gravity is so weak. That's because we're very far from the high density energy of this fundamental field that's carrying information across scales. And why would you want this model instead of the standard model? Well, you know, the Higgs mechanism only predicts 1 to 5% of the mass of the proton. Okay? The gluon field that's supposed to make up the rest of the mass of the proton is a field that mathematically is unsolvable. It's not analytical. We just run computers for years to try to solve these equations. They have no closed loop solution, closed form solutions. And the residual strong force is actually, mediated by these virtual pions. Virtual pions have never been measured. They're not measurable. All this is based on effective field theory, which is basically an approximation theory. It's like hand waving, okay? Renormalization issue, there's all kinds of infinities that show up in their equations that they have to constantly renormalize. And, there's all kinds of coupling parameters that are just based on like curve fitting on experiments. So, that's the current theory. What I just proposed to you is completely analytical. There's no free parameter. It's from first principle, and it does the job with more accuracy than anything I've ever seen, right? So that's kind of nice, just saying, right? And it was the dream of Einstein that you could geometrize space-time. All he needed was the energy of quantum vacuum fluctuation and understand how it decoheres across scales. When we did the calculation, I was, really excited when we did some final calculation on the Klein-Gordon equation, which are equations that are describing the gravitational, in this case, the gravitational waves interacting, creating coherency inside the proton and decoherency. And when we looked at the decoherency relationship, it turns out that it outputs the phi ratio. Okay? Just like out of the blue, just out of physics. There's only one other instance that I know where that comes out, and it's in thermodynamics of black holes. Davis published that a few decades ago. And so that was really exciting, and like that's nature, and this is why I went there, because like clearly in our paper we don't discuss that. We don't even mention the phi ratio. We just say, well, this is the ratio. But basically, this is for this conference, right? This links directly to nature, to the way nature developed. There's a direct relationship about how the vacuum decohere and how nature emerged from it. And so then that gives us hints to do calculation on it's called a spring constant, the coupling of the different scales, right? So we start calculating with William Brown, which we'll present just a little bit later. That's part of our team at our lab. And we calculated the scaling of this, like how it couples. Imagine the little Planck oscillator is spinning at very, very small scale, and then all of them together at the larger scale of the proton, and then again at the electron, and eventually making atoms and cells. And so we tried to see if we could match this scaling factor to what we observe. So we calculated the scaling factor based on the Planck frequency, and the frequency being omega, which is a spinning frequency, and then we calculated how this scaling factor of the coupling across scale. You all following me? Because I'm getting a lot of like blank looks, You guys following me? Yeah? Okay, we're good? Okay, so I know I'm going fast, but I only have 20 minutes. Did I blow it already? And so basically what we found is that we can scale from the Planck scale with this scaling factor, and we're nailing all of the frequency. Of course, for the proton we did because, I just showed you we do. But then, carbon, water molecule kind of necessary for life, benzene ring, tubulin, microtubules, microtubule bundles, and then the neuron. So we're scaling from 10 to the 43 hertz, okay, which is massive, right? All the way to like 30 hertz in the brain. Okay, showing that there's a direct relationship of the organization of the biological system, because starting at the proton, we're measuring, right? So those are values that are measured, empirical values, and we're nailing them all the way, and we end up at about 30 hertz in the brain, which is kind of remarkable. The idea, the foundation. I don't like giving talks so fast, but the idea of the foundation, because there's so many details I'm skipping that you guys need, but the foundation is that this fundamental field is the information field that's feeding the structure of space-time, all it needs to produce biological organization and eventually self-awareness, which is a feedback between the electromagnetic field and the gravitational field. So it's very powerful. We're writing papers on it as fast as we can right now on the biological side as well that we will publish. And I'm really excited to be able to share this with you this week. So that's me. Thank you so much. Thank you so much. There's a hand that's up. I don't know. Is there a mic? Maybe for the people online?
Test. Thank you. That was very interesting. I wanted to ask you, compared to the standard model, and seemed to say that, so you derived the the proton mass and these ratios of the, you called it color force to the gravitational force.
Yes.
You mentioned the fine structure constant, but I didn't hear any electrical force or weak force in your theory, so I wonder how it could be exact, or for that matter, the 3 generations of leptons that are in the standard model. Do you get that too?
What we get is a direct relationship to the electron. So you can get the electron, and it's just because I didn't address that in this paper and I didn't address that in my talk. But yes, you can use the same mathematics to get the correct value for the electron. It's exact. You can get these mathematics in gravito-electromagnetics. You can get these mathematics to actually give you the fluid dynamics of the field, and you get the charge from it, and the electron, the fundamental charge, the electron, and we haven't got to the leptons yet. And the weak force emerges as well from the interaction of the nucleons and the mass defect. So we can get that too, but we haven't finished that calculation, neither.
When you say those ratios are exact, you're including all those, it includes things like weak.
They're exact to the values that are measured for the color force, the residual strong force, the proton mass, and its radius, and all that's involved, including the charge of the proton, but that's not in that paper.
Okay,
thank you.
Hoffman hasn't shown up in cyberspace yet, so we'll go to William Brown. William Brown, and he's a good follow-up to Nassim. We're looking forward to lots of time for Q&A and discussion at the end.
Thank you, Thomas. Hello, all. I'm William Brown. So I've been working with Nassim Haramein and the research group at the International Space Federation. I'm primarily a molecular biologist with some training in biophysics. So my background is primarily in the biology aspect of what we're looking at. But I've been working with them on some of the fascinating solutions they're finding in unified physics. So bringing together general relativity and quantum mechanics. And we're looking at how we can explain key aspects of biophysics with that greater understanding of unified physics. I don't know if this clicker is on. The laser's working. Okay, so I'm going to be extending from Nassim's discussion and adding a little bit more detail to some of the points that he was touching on. So we have the understanding that quantum states are operational in the biological system, and they're leading to some of the correlates of consciousness that are associated with things like neuronal activity, primarily from the work of Stuart Hameroff and a great many others, but he certainly pioneered the field. And what's really fascinating about this mechanism, and why it's correct, is that it utilizes actually unified physics to describe the biophysics. It's, I think, one of the first theories that did this, which is one of the reasons why it's so ingenious, the work of Hameroff and Penrose. Now, one of the things is that it's discussing the underlying space-time geometry that's associated with quantum state. Or the mechanism of orchestrated objective reduction is primarily looking at the quantum state that is quantum superposition. But that's not the only quantum state that you can consider. There's also a couple of other really key quantum-type phenomenology that I believe are very important when we're talking about the subcellular dynamics occurring in the macromolecules of the cell. One such state that we can look at, the superposition state, how it relates to space-time geometry. I'm sure most people are very familiar with this in this room, just that you can have quantum superposition. It's going to have an underlying bifurcating space-time geometry. That bifurcating space-time geometry is unstable, and so you're going to have a certain time to collapse, the Diozzi-Penrose time to collapse, based on the energy that it takes to maintain this superposition in space-time, and then you get your reduction from a quantum state to the classical state. Now, one of the other things that we can look at, though, and aside from something like a quantum superposition, is quantum entanglement. And so when you have two particles that are interacting, or actually what has been discovered even very recently, when you have a collection of particles that are interacting, they become quantum entangled. And quantum entanglement is a strong correlation of a quantum system that is a correlation that goes beyond what you would find in a classical correlation of a system. So like if something is measured in one of these particles almost instantaneously, the other particle will reflect the measurement that was done irregardless of spatial or temporal distance. So that's also called non-locality. Now, that's non-locality in quantum mechanics. There's non-locality in general relativity as well, which Nassim described. And we saw that first from Einstein and Rosen, because they described a space-time topology that is multiply connected. And so that is, they did it to solve for the particle problem in general relativity, that a particle is a point particle, and actually in the standard model it has 0 dimension, and that leads to a lot of problems with the standard model. This is typically used to describe two space-time coordinates that are connected non-locally. In fact, you could have information transfer through this that appears instantaneous, even if the signal was going respecting the speed of light through the space-time geometry. Just because it's multiply connected instead of simply connected, it can kind of take a shortcut, and it can appear instantaneous. Well, that's what you see with quantum entanglement. You measure one particle, and its partner, that's an EPR pair. So Einstein, Podolsky, and Rosen also described this form of non-locality. You measure the property of one particle, and then whatever you measure will be almost seemingly instantaneously observed in the EPR pair, the other particle pair. The key to this, though, is to connect these two ideas. And so this was actually done. Now, probably Einstein and Rosen and his colleagues were connecting this, but they didn't speak about it publicly, at least. But this connection really came to the front with Leonard Susskind and Juan Maldacena, in that, we're going to model a subsystem, let's say a microtubule, with a bunch of interacting quantum states, quantum systems, or tubulin subunits, let's say. To model that as a quantum state, say we were going to simulate it with a set of computers, and your tubulin is your computer, let's say. and there's a great many number of the tubulins on a microtubule interacting. If we want to model that, let's say simulate it with a system of computers, you can't do it with a system of classically connected computers. So computers that are holding their own memory and sending signals to each other to process a computation, let's say, at the speed of light or below the speed of light. What you need actually to simulate something like a quantum entangled microtubule is the computers must be connected to a central memory nexus. So almost like the operations that are being performed are shared non-locally in a central memory nexus, and they need to be able to exchange signals quasi-instantaneously, just like you see with entanglement. That's to get a system, a network of computers to replicate a quantum system. Those are requirements. That's discussed by Leonard Susskind in detail. So we've got our non-locality in quantum mechanics, our EPR pairs. We've got our non-locality in general relativity. We could make a little jump and connect the two. And so now you've got a physical description for how you have entanglement in a quantum system. It's not magic. They're connected via multiply connected space-time topology. So there's quasi-instantaneous signal translocation through the space-time geometry. So now, if you have your network of computers, and again, I'm using an analogy of computers, but let's think of those computers as like tubulin subunits, and the network of them is a microtubule. In the brain, it works the same if we're assuming that they're processing information. Now, if we were thinking about it as operating classically, all those little tubulin subunits on your microtubule have to perform each calculation, each information processing event separately. But if they're quantum entangled, then one tubulin subunit can process the same amount as multiple tubulin subunits in the same span of a single information processing event. So this is called massive parallelism. And it's a key feature of our quantum system. So with entanglement, any one of your computational units can perform in a single go the same as a classical system with many of those same computational units. So you get massive parallelism, and this makes it so that if we're talking about quantum entanglement within the brain, each neuron probably has the information processing capacity conventionally attributed to the entire brain, just like a quantum system or even like a quantum computer would purportedly have the capability to do. And so this leads to some deeper understandings of the nature of reality, let's say, because what we have is that if we're talking about how these entangled subsystems are evolving over time, so let's say our microtubule is processing information over time as signals are coming into the brain, all that's happening really is that the overall wave function is evolving and becoming more and more quantum entangled. This is a key point because and the universe becomes just an immensely complicated network of entangled subsystems. And this is a key point because this entanglement is occurring via decoherence. So you've got an entangled EPR pair. How does it decohere? It interacts with another quantum system, and it becomes entangled with that. And that's called decoherence. But what is decoherence? Your entanglement network growing. This is a key point because a criticism that's often leveraged at like the orchestrated objective reduction model, or saying something like there's quantum brain biology, is that, well, your quantum states are too fleeting, too short-lived to have any kind of significance. But so if you have an entangled state, it's undergoing decoherence fairly rapidly. There is some logic to that, but what we're talking about with that decoherence event is the system becoming more and more entangled, exchanging more and more information, and that's actually a beneficial thing to happen. So the growth of this entanglement network, which often is leveraged as a criticism of quantum states in biology, is actually a strength of the model, let's say. And so, we've got kind of the conventional perspective of space as flat, and this kind of perspective, though, if we look at the finer scale resolution, it's actually like a quantum space-time phone. It's multiply connected, and our particles are EPR pairs connected by a Einstein-Rosen bridge topology. And the significance of this is brought out in the work of my colleagues of Nassim Haramein in the research team, in that they can output the key physical properties of the universe when they take this model into account. When you take into account that the proton is made from a quantized structure of space-time with zero-point energy, then from quantum vacuum fluctuations, then you can output key properties of the universe and key properties like the Hubble expansion constant, key properties of the proton like its mass, the strength of the strong force, the color force, residual strong force, Newtonian gravitation. And what you have is a information network made out of space matter, where the particles are little information nodes, little black hole information nodes in a multiply connected topology network. So this is showing the proton connected essentially to all other protons. And you can see that in the mathematics, actually. And we have previously touched on this in kind of a light way in a previous publication on the Unified Space Memory Network, so this is a network of nodal points connected via this space-time topology. So we call that a space memory, because it has the capacity to store information, to record information in the quantum state of space-time architecture itself. And we have touched on how that is related to consciousness, how you can get consciousness or aspects of consciousness from that. Extending the Hameroff-Penrose orchestrated objective reduction model, we have these entangled states, these EPR states that are connected by a wormhole topology. So now we can start to describe how entanglement along a tubulin could be the result of a space-time topology, essentially. And this is known as ER equals EPR. So your Einstein-Rosen bridges equals Einstein-Podolsky-Rosen correlations. So how would this scheme work? Now, I'll be going into this in a lot more detail in my talk, but essentially you have a quantum state that is that the microtubule is adopting as environmental information. Signal inputs are coming into the brain, being processed by the electrical activity of the neuron. It's being reflected in the global configuration state of the microtubule. The microtubule, this is key, is it's composed of quantum structure space-time. So it's imprinting its quantum state into the architecture of space-time at each space-time coordinate. So as we're going along experiencing things, so this is a space-time manifold here. We got one spatial dimension depicted, and we're going along on a world line. This is what you'll do today, let's say. And information's coming in, it's changing that configuration state. But that previous configuration state is imprinted, the quantum state that results in the activity of the neuron, which recreates the brain state, that, like the global electromagnetic pattern of brain activity. It comes from each neuron and the quantum state inside each neuron. That memory event, let's say at spacetime coordinate alpha, is imprinted into spacetime. You got things happening, the configuration state changes. You want to remember, you're at spacetime coordinate beta, you want to remember what happened at spacetime coordinate alpha. You are non-locally connected to that imprint in the spacetime structure via non-locality. So via quantum entanglement, that state is recreated in the microtubule morphology, and now you have recalled the exact state that corresponds to spacetime coordinate alpha at spacetime coordinate beta, and quasi-instantaneously you retrieve the memory of the information configuration of that spacetime coordinate. And that's pretty much a completely non-computational mechanism of memory, because the memory is only, let's say, superficially encoded in the microtubule. The memory is imprinted into space. You're connected to that memory imprint non-locally. So the memory, as you're recalling it, it isn't a process of computations. It's not like ones and zeros, bits being processed in the tubulin structure of the microtubules. It's that you can almost quasi-instantaneously pull the information from the spacetime coordinate that corresponds with the memory into your present spacetime coordinate, and the memory is just there. It's not like a digital recreation in that sense, because of the non-local connectivity. And so there's more to say on the mechanism of imprinting a quantum state of a molecule into spacetime, but again, just recall that under this unified physics solution, a particle, a space matter information node, is just the structure of spacetime in a very highly coherent phase. So it's not actually too much of a stretch to see how it's imprinting into the spacetime architecture itself. But in the solutions from Haramein and the research team, we can see where you have this high coherence quantum vacuum fluctuations generating the mass of the proton. The electromagnetic radiations from that high coherence phase is actually undergoing conversion to gravitational waves. And actually, they've computed that that exactly reproduces the Schwarzschild condition inside the proton, i.e. generates your black hole proton. And the Hawking radiation from that is the rest mass of the proton that you can observe, everything that Nassim was discussing. So that's one of the key things on the mechanism of memory imprint into space-time structure, is that matter is generating things like gravitational waves, and then you have things like the gravitational memory effect, gravitational wave memory effect, which I'll talk about in more detail. But the inside of that of the matter is that high coherence quantum vacuum fluctuation energy density. That's what we have here, the quantum vacuum fluctuations. And just to really drive home that we are, fundamentally, that is what we are constituted out of, and that's one of the reasons why we believe we can derive from that ultra-high frequency oscillation of the high coherence phases of the quantum vacuum, the frequencies and oscillatory characteristics across scale going up to the brain, ultimately. It is coupling of biological structures with fundamental space-time architecture via Planck pulse frequency resonance chain of coupled oscillators. And so essentially what you have is a high-frequency oscillator that's coupling to a larger system, transferring energy into the ground state oscillations of that system and activating it. That's actually almost exactly how a neurotransmitter works. You have a little neurotransmitter that binds to a neural receptor, and The neurotransmitter is a whole high frequency has high frequency oscillations. Those high frequency oscillations are transferred into the ground state of the neuronal receptor, and it activates, and you get a neuronal action potential. So we're looking at the coupling that's occurring at that fundamental mole scale with the space-time voxels, the information quanta of space-time. And this coupling that's occurring, this is an interaction. So again, these are entangled in forming a space-time topology. And that space-time topology extends, multiply connected topology of Einstein-Rosen bridges, extends from our small scale of the quantum structure of space-time up into the cellular scale, the multicellular scale, and even the neuronal, the tissue scale. Which we see because we can output almost exactly these values. We have water highlighted here because of the significance of water in facilitating not only the information coupling from the coherent quantum vacuum fluctuation of spacetime to the larger molecular architectures, but even in between molecules, water in high coherence domains functions essentially as a negentropic converter, where as part of the information transfer process is an area of low entropy, essentially ultra low entropy, and that low entropy is being transferred primarily via a coherent structure of water into the biological system. We can see how within the proton this is these high coherence phases are going to less coherence phases, and we can actually follow the entire progression of this resonance chain of coupled oscillators, going from the core of the proton, and we get the typical frequency for a black hole-sized proton, the typical frequency, the strong interaction time for a proton, and it's being scaled via this very specific ratio. But we can also see how that goes to multinucleon states, so the alpha particle helium nucleus. Then now we're getting into the biologically relevant scale. 3 alpha particles come together to give you a carbon nucleus. 6 carbon nuclei come together to give you a benzene ring type structure. This is actually your quantum emitter within the microtubule, your tryptophan moiety, which is one of your primary chromophore oscillators involved in the information processing in quantum state of the microtubule. But we output almost exactly the terahertz type frequency that characterizes that. So all these can be compared to measured values. So this is just the significance of the aromatic amino acids in the tubulin and microtubules. You have them like tryptophan embedded in each tubulin monomer, and then they come together to form what Philip Currian calls a mega architecture of tryptophan oscillators across a microtubule segment. And then we can output gigahertz frequency, megahertz frequency for the microtubule, then microtubule bundle, kilohertz frequency, all from our equation there. And then if you take the mass, average mass of a neuron, a neuronal cell, and you put it into our equation there, we get approximately 30 hertz, which is one of the lower frequencies of gamma oscillation. And these have also been, all of these have been measured by like Anirban Bandyopadhyay with the triplet frequencies for a tubulin going from terahertz, gigahertz, megahertz, microtubule, gigahertz, megahertz, kilohertz, and so on. Same with the neuron, triplet frequencies. And that's what we see in our calculation being driven from this Planck pulse frequency of a coupled chain of nested quantum harmonic oscillators. And then that kind of information transfer can drive the behavior of microtubules, which ultimately drives the behavior of brain states, which correlate with conscious experience. Thank you.
Thank you so much.
Thank you.
So next we have Suzanne Gildert talking about, is that a question for William? We're going to take questions at the end.
No question now?
Right. Okay. Suzanne Gildert talking about testing for conscious agency in quantum robotics.
Hey, everyone. Nice to be here. Thanks for Stuart and the other organizers for giving me a chance to talk at this conference. And today, hopefully, I'm going to explain how all of you guys are going to help the future of AI and robotics be more aware, empathetic, and safe. I want to start with a little bit of a backstory about myself and how I got interested in this in the first place. So I'm originally a quantum physicist, but I worked in the humanoid robot industry for about 12 years now. This is an example of one of the humanoid robots that I work with, along with some awesome colleagues at my previous company, Sanctuary AI. So we built these systems and we tested them, we connected them to AI algorithms to try and get the robots to behave like people. But what we discovered is that getting AI to work on physical robots is extremely difficult, and this is a problem that plagues the entire humanoid robotics industry. AI struggles to learn, and it can't deal with edge cases or complex environments. So you can take something like a humanoid robot, say working in a factory, and you can train it to do one task, maybe a pick-and-place task, and it will do that very nicely. But a humanoid robot is supposed to be general purpose. It's supposed to be able to take what it's learned from that one task and apply it to general purpose environments, just be able to go out there into the world and do any task we want. We find that that does not happen. These tasks do not generalize very well to the kind of complex, dynamic environments that humans are so good at navigating. So the question I asked myself when I was researching this is, how is a human mind different from embodied AI? And the answer is here in this very room today. We are conscious, and everyone at this conference is here, hopefully, because they're interested in consciousness and understanding what it is and understanding more about it. So I think what we need to do is connect this research community to the AI and robotics research community more and get those people as fascinated by consciousness as we all are. I'm going to simplify things a little bit here, but our mind typically has two modes of operation. We have autonomous decision-making. You can think of this as sort of zoning out or muscle memory, say when you're driving along the highway thinking about something else, you're not paying attention to the driving. But then if something unexpected happens, we switch into this conscious, hyper-aware mode, and we go into conscious decision-making mode. All AI today operates in the first mode. It's shown thousands or millions of examples of training data, just like we are when we're learning to drive, and then it runs on autopilot. It doesn't have this conscious decision-making ability like we do. So I think this is very important for AI because we're missing half of what our brain does. And as an analogy, if you like, you can think of the left hemisphere and the right hemisphere. If we're building AI, we've basically only been building one hemisphere of the brain so far. So let's think about consciousness. AI needs to explore new theories. The theory I'm most interested in, which is quite well represented at this conference, is quantum consciousness hypothesis. And so this is actually quite simple to start integrating into AI and testing. The autonomous decision-making component that I talked about can be handled by classical computation and classical learning. But this conscious decision-making process can be handled with quantum computing. And that's the new part. That's what we want to test. So normally people think of the way the human mind and human control works is you have a human body and a human brain. Perception data comes into the human body, goes into the brain, somehow magic happens, some computation happens, we're conscious, and then action comes out of that brain. But the quantum consciousness hypothesis says that there's not only one route through the mind, there's actually two routes. One of them is a classical loop, which handles our autonomous decisions that we've learned over time, and the other one is a quantum loop that handles things when we're in an unfamiliar environment, when something unpredictable happens, and we have to become hyper-conscious of that. Most quantum consciousness researchers are testing the ideas in biological systems, such as microtubules. And there's a nice little artistic rendering here of some microtubules in the background. But we want to try a different option. We want to give robots a quantum brain to see if we can learn anything about consciousness and agency through this second route. Quantum computers are here today. So believe it or not, you can actually go online, sign up for an account, and access many different quantum computers offered by many different quantum computing companies today. So people who know programming can start to get into quantum programming as well. Here are just some of the examples of quantum computing companies, and many of these offer an API service now where you can actually log online and use a quantum computer remotely. Can quantum computers help us test the quantum consciousness hypothesis? So let's go back to our diagram of the human body and the human brain. We have these two loops, the classical loop and the quantum loop. What we're going to do is replace exactly the same two loops, but replace the human body with a robot body and replace the brain with AI systems. And you don't need really complicated robots to do this. So this is one of the research robots that I'm working with today. It's a small, mid-level robot. It's not really a toy, but it's not a professional-grade robot either. It's somewhere in the middle. But what I want to show is that, for a few hundred up to $1,000, you can put together a simple robot system that allows you to test quantum consciousness experiments. I'll be running this as a demo during the conference session at the lunch breaks and things, if anyone wants to see the actual robot demo in action. So when we put our robot into a loop where we have the classical part that handles the autonomous decision-making, we expect there to be no experience there. There's no first-person subjective experience. But if the quantum consciousness hypothesis is true, once we plug the quantum computer into the robot, the system will actually start experiencing. So this is the cool idea. So it has an observer, it has a first-person experience of the world. The problem with that is, as we all know here, first-person subjective experience is impossible to get at. I cannot go inside your brain and know about your subjective experience, and you can't do the same with me, and I can't do the same thing with a quantum robot. It's inaccessible. But what is accessible is monitoring the outputs of the robot, the behaviors, the actions that robot takes. These are something we can measure and compare when we run classical versus quantum experiments. So I want to dive in a little more detail into how AI systems today turn the perception into action so we can compare it with a system that might be conscious. Most AI systems that are embodied, which means they're in control of a physical body like a robot, use something called reinforcement learning to learn how to act. Many of you may be familiar with this, may have heard of it. If you're not, the way reinforcement learning works is the robot tries a bunch of random actions, and then it's given something called a reward function. So think about this like training your dog. Every time your dog does something you like, you give it a treat. This is what we do with a standard reinforcement learning system. Every time the robot does something that we like, we give it a mathematical treat, mathematical reward. The problem with reward functions is that they have to be programmed. So I, as a programmer, have to sit down and tell the system what's good and what's bad. That's very difficult when you've got a general purpose robot because it has to do thousands and thousands of different tasks, so they're hard to program. The other way you can get a reward function is you can learn it by watching human demonstration. So the most state-of-the-art embodied AI systems today use something called imitation learning, where a person actually teleoperates the robot, gathers many, many, many examples of what the robot should do, and then the AI learns from that. So it's essentially like a child learning by watching what the adults do. The problem with that is you need huge amounts of training examples for that system to learn from human training data. Okay, so that's the classical reinforcement learning system. What we're going to do with the experiments I'll describe is replace that with a quantum AI system. And the next thing I show is going to be the thing that makes everyone gasp if they're not coming to a Science of Consciousness conference. But you're all going to be okay with this, because it's totally right. Quantum consciousness, one of the things about the theory states that when this collapse of the wave function process happens, there's actually an agency in the system, a free will decision, if you like. So what this means is that when the quantum computer does the computation and this wave function collapse happens, it actually makes a decision that seems to come from nowhere. The universe decides, if you like. The quantum conscious agent chooses the action for itself. I'm not programming it in. No reward function is needed here, and no training data is needed. It's as though the system just knows what to do somehow. So I'll leave that open to all of you to think about how it might know that. This reminds me very much of life. So at home, I have a little microscope, and I watch these pond creatures, these paramecia and their friends under the microscope. And as Stuart is a fan of saying, these guys don't have a single neuron inside there. They're a single-celled organism. So they have no neurons. They have no classical AI. There's no neural net to learn anything. So how are they making decisions? Well, one theory is that their cytoskeleton inside them is actually a quantum conscious computational process that's hooking into some kind of universal reward function. So the question is, does life already have this built-in reward function? Can we learn something from these teeny tiny creatures and apply it to AI systems? Is this where instincts and feelings come from? Is this what gives life, creatures, and us a sense of curiosity and creativity? And is it what gives us that deep down will to live? That desire to be here and experience things rather than to not be at all. So, if life has all that, might our quantum robots also inherit this built-in reward function if we're constructing them in the same way that life constructs our experience and our agency? I'm going to talk about 2 experiments that we're doing at Nirvanic to explore some of this stuff. So the first experiment is that we take the system I described, a robot connected in a feedback loop with a quantum computer, and we keep everything exactly the same, but we replace the real quantum effects with a simulator. So this is a simulator of a quantum computer, but it's actually a classical system. Does a system in this feedback loop choose the same actions in the case of the quantum and the classical? This is actually real data from the action choice that I measure as the robot runs this feedback loop. Experiment 2 goes a little bit further. So say we do see a difference between which action the robot chooses when it's quantum versus when it's classical. So let's take our system again with 2 cases. Now we add 1 extra component in. We add this reinforcement learning system that I talked about. So now the system isn't just choosing actions, it's actually learning from what it did. So you can see in these 2 instances, this looks exactly the same. So the output should be identical, but in the case of quantum consciousness, there's one extra thing that's hypothesized, which is this built-in reward function. So in this case, you've got a programmed reward function, and you've got this built-in reward function giving it a boost, giving it some extra intuition, some extra ability to make smart decisions. What will happen? I suspect that the learning rate will be different in these two cases. So what we'd hope to see, if the experiments are successful, is that you'd see a boost in the learning rate in the quantum case versus the classical case. And that difference is coming from this built-in agency that the universe has that allows it to make smarter decisions compared to it just trying random actions. Designing these quantum conscious agents, as they're called, that work in the software backend is quite difficult, but it's something we can start doing today. This is a very simple example of how you might go about starting doing that. This is a simple quantum neural net. So many people may be familiar with artificial neural nets. You can build quantum neural nets in a very similar way, but you use qubits instead of neural units in the network. So the way this system works is you have some input qubits, and these get the data coming in from the robot's perception system. So you take something like vision features coming in from the camera and send them into this neural network through some kind of mapping function. And then the neural network puts everything into a superposition in an entangled state, and then you run the quantum algorithm and the system collapses. And when it collapses, it chooses values of these output layer qubits. And these outputs are connected to the action modalities of the robot. So the robot takes an action based on what the quantum neural net ends up collapsing into. So here is a little video of this in action, and I'll actually be able to show you this demo live a bit during the conference, but this is a very simple setup where we've taken the robot and we just have it like looking at different points of interest in the scene. So it's looking at some numbered labeled areas in this visual field, and we're monitoring which action it takes at every step. And the action is just where it chooses to look. I think there's like 16 different options for where it can look in this case. And you can see it gathering statistics. So every time it makes a choice, we record that, and we monitor how this action distribution looks over thousands and thousands of measurements. The idea is that if you run the quantum system and you run a classical simulation of it, these action distributions will be different. And what we're looking for is a meaningful difference. So here's some actual data from the experiments. Now, someone might look at this and be like, oh, they're different. That means, quantum consciousness is true, yay. But don't be so hasty and fast. There are many, many, many reasons why this might be different. Quantum computers are incredibly difficult to work with. They can be noisy, they can have errors in them. So the problem with this is you have to be very, very careful with what you're doing. The other problem is that these systems have hundreds of different parameters. So I'm just very boringly going to go through a few of them with you, and then you have to try and imagine that there's hundreds more of them. So the number of layers in your network can be varied. Here I've shown 3. You could have 50. Any number in between. The collapse rate can change. So when you run this quantum algorithm, there's a number you specify in the code, which is how fast the superposition forms and then collapses. That's also a variable. Noise in the system. I mentioned quantum computers already have noise, but you can actually introduce some artificial noise to make the neural net a little more chaotic, a little more exploratory. That's also a parameter in the algorithm. Feedback. Do you just run this neural net in a forward pass, like most artificial neural nets do today, or do you include some kind of feedback where the units learn from their previous values? That's another parameter. Input features. I mentioned the webcam. You could have any number of different signals coming from all over the robot's body: vision, audio, haptics, proprioception. As a designer of a quantum conscious agent, you have to decide which of those features make it into this quantum network and how do I compress them before they go in. And then similarly, the output encoding. You have to decide when that quantum state collapses, what do those numbers mean? I get a bunch of +1s and -1s out. How do I connect that into the robot's motor system? So hopefully here I've just given you a tiny slice of an example of some of the parameters you have to consider when designing these quantum conscious agents. This we have to be extremely rigorous about and extremely scientific about. I like to liken this phase that we're in with this research as being similar to pre-2012 era of deep learning, where people hadn't really discovered the right parameters to put into their neural nets to come up with things like general purpose transformers, which is the technology behind ChatGPT. So we're right back at that early phase where we're trying to design very small versions of these quantum neural networks. We're in the very early phases of understanding how to craft these quantum conscious agents. But as I've shown you with these variables and different ways you can change the system, there's almost an unlimited amount of exploration that can be done using this platform. Maybe we'll discover consciousness with it. And just to finish, I want to give you a view for the future. So I've worked in humanoid robotics for a long time, and the first thing anyone usually says to me is, oh, you're building Terminators. Like, please don't do that. But I see a role for consciousness and self-awareness in robotics that can actually make them safer and make them more helpful to us. David Chalmers talks about the philosophical zombie. With current AI, we are building philosophical zombies. We're not building conscious, self-aware robots. We're not building systems that could have true empathy, true emotions, and true understanding of what we are feeling. So I think quantum consciousness research in general, when married together with the field of AI and robotics, can make robot systems that we really love, we fall in love with, and we actually want to interact with as people. So thank you very much, and if you're interested in learning more, you can follow us at Nirvanic AI, and we have a Substack newsletter as well. Thanks for listening.
And where are you going to demonstrate that?
We have a little table in the demo hall during the conference, so we'll be there kind of on and off showing the demo.
Wonderful.
Yeah, and he's called Kit Kat, by the way.
Called what?
Kit Kat.
Kit Kat.
Yeah.
Thank you so much.
Thanks.
Okay, next we have Nestor Mercado talking about space-time crystals.
All right. Essentially, I think we live in a space-time crystal, and that these nodes that everyone kind of keeps on circling around, we're connected to something. I think they're little space-time crystal nodes. But before I get into that, I think memory is fundamental. Right now, you're listening to me, and sounds are going inside your ear. You're trying to make sense of what I'm saying. But to perceive, you must be remembering. They're always coupled. And that is always true, no matter what. I think to be conscious is to be aware, and to be aware is to perceive. And to perceive is to remember. So even after life, after we die, if we believe that there's something afterwards, I think we kind of had an intuition. It's what they drew in the drawings with the halos, right? Think of those halos as memory units. Or think of the same thing, but it's kind of like, it's divine halo. I think we all have that. And I think it's encoded, I'm going to be really technical, I think it's encoded in the magnetic vector potential that's everywhere, all around. It's the Aharon-Bohm effect, which I won't get too much into that because that's too technical. But essentially, I got to read that. Give me a second. Essentially, space-time is always vibrating. It's oscillating. Think about it. General relativity tells us that no matter how much mass, no matter how much energy, it could be a feather, It's perturbing space-time. Space-time is oscillating, and it's dipping, and then it's going back to some equilibrium. It doesn't matter how much. That's just what happens. Quantum field theory asserts that even in empty space, there's still energy, there's still fluctuations occurring. So we can say, according to our best theories, that space-time is vibrating. And if it's vibrating, we're not just in space-time. We're not just hanging out in space-time. We're coupled to it. And if we're coupled to it, that means we're all touching the same thing. We're all non-locally coupled. And I think that's a fact. And I think that will be later on, sometime in the future, hopefully not too long from now, we'll start realizing, hey, it's vibration, they generate waves, waves interfere, and once they interfere, they generate geometry. It's not the other way around. Everyone keeps on talking about geometry, which is cool, but it's about vibration first. Okay, this is the only thing I'm going to read off the top of my head, or I just have to read this out loud, sorry. Okay, so I've been exploring the idea that memory is more than recall. It's the persistent influence of past states, and it's encoded in the phase structure of nature. Memory acts as the reference frame that gives structure and context to incoming information, allowing it to be interpreted meaningfully. Phase seems to govern not just evolution and interference, but coherence itself. Forces seem to emerge from the need to preserve local phase coherence. And gauge theory, it starts to look a lot like a memory preservation framework to me. I'm convinced that observation is also a kind of gauge transformation, where phase alignment determines what gets encoded, what metric gets built/experienced, and what gets lost. A kind of phase Doppler shift, because we're never not moving. Even if we're standing still, we're performing Doppler shifts right now as we speak. And Doppler shifts, those are phase shifts. It gets technical. I'm almost done. And more, I see all physical quantities, energy, momentum, charge, mass, even space and time, as different ways phase expresses itself. Gradients, constraints, interference patterns, math too. I think every single thing in math that exists right now, I think it's just syntax describing phase dynamics. So if you remember, go home, ask your GPT to think of any type of math that does not relate or cannot be described using phase dynamics. I don't think you can find it. Which is to say, if all you had was phase, and you asked, how could phase vary? You'd get time, space, waves, interference patterns, geometry, forces, fields, particles, and the laws that govern them. And if that is true, then phase is nature's language. It's the way nature speaks to itself. But before that, it's memory. Phase is memory made manifest. It's both memory, it's both the medium of information and the memory structure that ensures its preservation, continuity, and ongoing influence. Okay, I got that out. All right, so space-time is always oscillating. I can't think of a real scenario in which it doesn't oscillate. Gravitational waves, you have a frequency, it generates a wavelength, we got a gravitational wave. And under any real condition, I think space-time, it's like I keep on repeating myself, but it's oscillating. And if it's oscillating, that means that all of us, we're spatial structures, we're more temporal structures. We're encoding our memories, but we can compress time. We're like cool that way. So if we think of planets as these giant things, it's like they're nothing compared to us because we're compressing time as memory. So we're really the largest structures in the universe. And the thing about time crystals is that time crystals were a form of matter that were discovered / made in the 2000s. And essentially, they put a frequency. That frequency generates a lattice structure. You change that frequency, it generates a different type of lattice structure. Essentially, it's the frequency that generates the structure. So the structure repeats, not in space, but in time. And I think we have all the hallmarks when you think of it. That's what we are right now. That's why we see fractal patterns. That's why we see, just think about it. This is a very simple form of Einstein's field equations. Essentially, on the left, if you have mass or energy, it has to affect the right, which is the geometry. You have mass or energy, you do this, and it affects geometry, always. And it doesn't just get there. It's a wave. It's a vibration. Vibration's a wave. Those waves interfere, and they generate geometry. It's always that way. I keep on saying phase. Phase in physics is kind of boring. It's kind of you get this phase diagram. If I were to ask, what phase is that wave? I'm essentially saying, where is that wave in its cycle? So I might say, hey, what's its phase? And it might be at the top of the crest. So that would be an angle. Or it might be at its lowest, which might be its trough. That's how physics talks about phase right now. But it's more than just that. To ask what phase something is to assume that it had a before, that it has a now, and that it has a future. That's why it's in our wave function. I mean, you look at the wave function, the most important thing there is phase because it's what brings the structure along. Which is a form of memory. Remember, memory, it's the ongoing influence of past states. This wave has been affected by other things that it ran into. When we're asking what's its phase, we're just asking what is it right now? Because whatever it is right now, that's its state. And it's kind of like our memories. You are who you are right now because of everything that has occurred to you. It's the same thing. Even here, these were moving, but not anymore. If I were to ask a sundial, this sundial moves, and I say, what's its phase? It's at the 3 o'clock position. It's essentially asking, what time is it? It's 3 o'clock. The Earth rotates. If I were to just say, stop, oh, where are we? We're wherever we are right here, in the Atlantic Ocean, in the middle. Even our Earth orbiting the sun, you could be thinking about it the same way. So phase offers kind of a sense of time. Time becomes the accumulation of phase. Remember, every single time we ask, what time is it? What's this time thing we're talking about? We're always, without question, we're asking ourselves something about frequency. Whether it's the day repeats 24 hours, whether it's a year, 365 days, whether we bring an atomic clock and take it up into orbit and we say, hey, how much time has changed because of Einstein's equations? We're saying how much frequency of that atomic clock has increased because when it was here on Earth, it wasn't vibrating as much. We bring it up to Earth or to orbit, it starts vibrating even faster. It's not succumbed by the forces of gravity. Time is always periodic. It is always cyclical, but it's ongoing. It doesn't just reset after a period. So in that way, time is the accumulation of phase. All right. So let's just imagine before the Big Bang or the Big Breath is what I like to think about it. You're in a universe where you can't make left from right. You can't even make sense of anything. It's just this, it's like a bad acid trip. It's just, you don't know what's going on. So you can't think of, you have no reference point. You have nothing to make sense. Everything is happening, but nothing can be said about it. That's what this is right now. Until we have a coherent, finite energy. You see, once you have finite energy, you get a maximum frequency. If you have a system and you insert finite energy, that system can only oscillate, vibrate at this frequency. You can't go anymore. That's what our equations say. If we isolate that system here, if you were to inverse of that frequency, take its inverse, then you get the minimum time, the minimum moments. Essentially, finite energy says you can only go this fast, and your moment can only be this much. It also says that your scale, your minimum scale, can only be this much. If you complete one oscillation, you get a scale, which is the wavelength. You don't get anything less than that. That's your scale. You can't have 1.5 of that. Those are your increments, because that's finite energy. So let's pretend we have finite energy here. We say finite energy gets us a frequency. That frequency says, this is a fancy way of saying frequency. Remember, every single time, frequency is just the rate of phase change. When we're saying frequency, frequency is not a thing. Frequency is describing a thing, and that thing is phase. And that's how you write it, the d phi over dt. So finite energy gets you finite frequency. Same with time. This is time minimum. This gives you the temporal scale. So right now, if we say there's been 1 cycle, 2 cycle, 3 cycle, 4 cycle, this universe, there's no space-time. Remember that. Space-time doesn't exist. But if I were to say, hey, we're on that 4th wave, how much time has occurred? You might say, well, there's no time. And I'm going to say, yeah, not in the typical sense, but how many waves have occurred? 4. Okay, cool. And each wave has this amount of scale. So we'll say there's been 4 time scales. 4 waves times t, and that's a special number. So we have a sense of duration. We have a sense of before, after, a continuity, kind of like an arrow of time built into phase. If I were to ask, well, okay, we're on the 4th wave. How far have you gone? You might say, well, there's no space here, man. All right, not in the typical sense, but we have a definition of what a length is, and it's right here. So you might say, 4 cycles, multiply that wavelength times 4 cycles, that gets you a duration. So now we say, cool, we started off with no space-time, but now we have space-time, at least some form of it here. We have momentum too, which is important. But what if we started off with finite energy, and now we have time and space, which is the really, really important things. But if we let this thing just keep on going, it's just going to dissolve. I mean, there's no boundaries. It's just going to dissolve, but that's not what nature does. Nature's efficient. Nature likes to stabilize. So I think what would happen is the most stable form of change is change. So it's going to change. It's going to go from one direction to the y direction. It's going to generate another dimension because it's more efficient, more stable. Ooh. So now imagine that it generates another dimension. You're going to see patterns, waves hitting, becoming more richer patterns occurring. And that it allows for more information to occur, more information to be generated. But before I speak to that, this is going in one direction. If I were to ask, well, how fast is this going? You might say, well, we have time, we have space. Nestor, why don't you just multiply frequency times the wavelength? That'll get you the speed of this, whatever this thing that you're describing. And I'd be saying, yeah, I think that's it. That's how we get the velocity. Let's imagine that frequency was Planck frequency, the highest oscillation that can ever occur. And we multiply that by the wavelength. Let's call that the Planck wavelength, the minimum wavelength. If I were to say multiply frequency times the wavelength, we get the speed of light. We don't just say it's the speed of light. No. In this universe, nothing can go faster than this oscillation. This oscillation sets the maximum rate at which anything can change, and that has an associated spatial length. That becomes the speed of light. Normally, when we talk about the speed of light, we're talking about, it's like picking a number 5 at a McDonald's or something. You just pick and choose what wavelength you want, what frequency you want, and you call it, as long as it's the speed of light, you call it fundamental. I don't think that's fundamental. Why would it be? Fundamental to me sounds like something where the universe limits how fast anything can change, which has an associated wavelength, which sets the rate at which anything can travel velocity-wise. And that all comes from finite energy. I think we need to start thinking about finite energy more instead of thinking about infinities, because this right here gives us so much. If we can't go to zero because space-time won't allow us, that opens up a whole new world. Or we can keep on going to zeros and going to blow-ups. But I don't think that makes sense. All right. So we went from one dimension. We said, hey, well, we need to let that dimension move around, get more polarity, introduce polarity, because that's what 2 dimensions would do. Once that occurs, hey, Nestor, you got 2 dimensions, but if you let that energy flow, it's going to dissipate. And I would agree with you. And I think that's why the most stable form of change is change, so it would have to change again to 3 dimensions, which would be something looking like this. And when it does so, you start thinking, well, what does this look like? It starts looking like a crystal lattice, a space-time crystal lattice made up of one field, and I'm calling it the magnetic vector potential with units of Weber. But it moves. This little thing right here is the quantized version of that magnetic vector potential, essentially vacuum energy. Imagine vacuum energy being quantized because the universe is finite. I mean, it would have to be, but then you get this cool little space-time crystal node that's holding everything together. Something like this, but not exactly perfectly rectangular. Okay, which is to say that I think the Planck units are telling us something. I don't think you have to do all this square root times c to the 3rd power to the h. I don't know. I think they are what they are. Take Planck mass divided by Planck length, but let's say Planck length. Let's just call that Planck radius of the little nodes. Planck mass divided by Planck radius, what do you get? You get c squared over g. You don't have to do any fancy semantics. That's just what it is. It's the curvature of that node. It's the maximum curvature of that node, and it just equals that. I don't have to do anything special. I don't have to sell you anything on that. Now, let's say, hey, let's get the gravitational potential of that little space-time crystal node. All of a sudden, you do mass divided by its radius, put the little g on there, which, by the way, was defined. All you have to do is just move the g around, right? Not really a lot of math, it's a lot of algebra. But look at the gravitational potential of one little space-time crystal node, which is a quantized vacuum energy packet, it's equal to c squared on the surface. It's just what the algebra shows us, right? We never look at it that way because we're so confused. We're so preoccupied saying the square root of h bar 3 times whatever. I don't even know what it is. But this also says something else. If you were to take the inverse of this, you would get 1 over c squared. But even before you do that, this right here, the gravitational potential of a little space-time node is equal to c squared, which is also equal to 1 over the product of the electromagnetic constants. That's all built inside the space-time node, which I think as soon as you get that 3 dimensions of this energy and it closes off, the first structures that exist are these standing waves. And those standing waves are the nodes in this space-time crystal lattice that we live in. Those are the first structures, but they're made out of vacuum energy. And vacuum energy is like this mysterious thing that is just so hard to measure directly. We always have to infer it. But I think that's what it is. If you take the inverse here, you just get g over c2, which is essentially the gravitational constant multiplied by the epsilon naught and mu naught. There's something fundamental going on here. There's no hand wavy. This is just what it is. And I think we should remember that. So we always talk about time dilation, but what if we live in this space-time crystal lattice and the nodes are made out of these wave packets of vacuum energy? Then when we're doing our frequency, our time dilation experiments, what's actually happening? Well, maybe what's actually happening is that the gravity is essentially pressing down on the oscillation of these wave packets. So now, remember, time, how I've described it, is just the accumulation of the phase. But if the phase has been dampened, it's not going to be vibrating that much. That's what's going to be time dilation. Go to your GPT and say, hey, let's not call it time dilation. Let's call it frequency dilation. See what you get. Explore that. And these nodes are very, 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 very small. I'm seeing it with these presentations. We're all talking about the same thing, I think. I think we're talking about networks. That's what this is. This is a network. It's a network of space-time crystal lattice nodes. And it's because, remember, it's vibration. Vibration generates waves. Waves clash into each other. They interfere with each other, and they generate structures. We're stuck over here and talking about geometry this and geometry that. And like I said, I'm making the claim that any mathematics can be described as phase dynamics. So I ask you to go home and put, if you're a mathematician or whatever, say, describe whatever math you want to describe as phase dynamics. It might say it can't do it at first because it's not accustomed to thinking this way, but say, are you sure? That's all you got to say. Are you sure? Are you sure? And I still can't find mathematics that can't be described as phase dynamics. I still can't do it. So if you can, it should be easy to do. You should be able to do it in the next 30 minutes and come up to me and tell me I found it. Again, we started from void. I call this void because it's just, there's stuff in there. It's just, except nothing can be made sense. You can't make sense of any of this until you put finite energy. Because finite energy is what gives things structure. Remember, finite energy is what gives things structure. You can't be talking about change if it's not finite. Just period. It's impossible. Change is undefined if it's not finite. Information is undefined if it's not finite. And like I said, since everything is phase, then everything can be encoded in phase relationships. I'm even saying mathematics, which should be easily true, should be disprovable very easily. And if everything is phase, then everything, that's the informational substrate, because phase has a before, it has a present, it has an after. It has a built-in self-referential thing about it. That's what phase is. It's not said that way, but it's definitely there. Remove phase from from the wave function, see what you get. Remove phase from just all our mathematics. Remove phase from particles, it's all gone. You remove phase, you don't have a universe anymore. Remember, time is just the accumulation of phase. Space is just relationships of phase, polarity. That's what happens when you get 2 dimensions. 3D is what happens when you let phase generate 3D and close off, because that's when it has boundaries. And the standing waves are the space-time crystal lattice nodes that I think are magnetic vector potentials. They're the vacuum energy packets. And that's why the numbers work so well. I'm just repeating myself here again. Notice how the phase looks like a clock, because it is. 2 dimensions. And what these become here, these spring-like, you guys ever wonder, the gravitational constant, it has units of meters cubed per kilogram second squared. That might sound crazy. I always wondered, why does it have these strange units? Gravitational constant has meters cubed, kilograms per second squared. It's because it's talking about 3 dimensions of spring-like behavior. That's what these space-time nodes, that's what these are. It's 3D spring-like, it's a restoration force, and it's also a spring-like force. It's all of that. I'm not sure if I'm too early. Am I too early? 2 more minutes? Okay. Okay, so essentially I talked about memory. I think memory is fundamental. I literally think that the microtubules, I think they're generating magnetic vector potential patterns above our head, literally above our head. And I think nature chose to do this because chemicals are so, it's not, anything can infect us. We can get sick. But our memories, the good stuff, the stuff that's on the magnetic VHS tape, or that's on the cloud, that's going to be encoded in the cloud, or the magnetic vector potential. And we all have it. And the only way to interfere with that magnetic vector potential is to interfere with the source, which would be to interfere with the microtubules. To interfere with the microtubules, you're going to have to put someone to sleep, or you're going to have to kill them. And I think nature, we talk about complexity. There's this paradox of complexity. Just imagine that phase diagram. It's not a paradox. It's the fact that we're evolving, but we're also generating more information. And that information is being encoded in memory to generate more stuff. It's just like when we're on the internet and we're doing whatever we're doing. And they generate new games for us to play, new programs to play. Things are getting complicated, but our interactions are being saved, and those are generating new programs, new AI. It's getting complex, but it's also fighting this entropy thing that we keep on talking. It's not really a paradox, it's part of everything. And I think one of the gentlemen was talking about it today. Anyway, yeah, the halo thing, I think it's real, so just remember that. I really do think it's real. That's all I got. Thank you.
Thank you. Okay, we're going to have a quick break. I think a 10-minute break. How about a 10-minute break? And then after the break will be Stuart Hameroff, and we're still hoping to get Don Hoffman online. So 10-minute break, and then we're back for Stuart Hameroff, then me, then Don Hoffman, hopefully, and discussion. Okay, we're about to start. Our 15-minute, 10-minute break is over. And next we have the leader of this whole conference, Stuart Hameroff. So I'm very excited. And after that, I will go, and then we'll have a panel of all of us up here. So speakers, be ready for that.
All right. Thank you, Thomas. Thank you all for being here. It's been a great session. And I'm going to talk about whether consciousness is fundamental from the ORCH-OR perspective. And ORCH-OR is the theory I developed with Roger Penrose. And on my first slide is his book, written in 1989, The Emperor's New Mind, and which was kind of a slap in the face to AI, which was claiming that just more and more computation would inevitably lead to consciousness. And the emperor, I think at that time, was Marvin Minsky, who was the leader of AI. And he was supplanted by Kurzweil and many others now. And now, of course, AI is just steamrolling and trying to convince everybody that it will be conscious inevitably. And even David Chalmers, who championed the hard problem, has kind of gone along. So I don't agree with that, and people have expressed it. I think AI can be great. LLMs are super. But to be conscious, I don't think so, at least not as presently constituted. So what is the ORCH-OR perspective? Well, let's start with one of the main problems in quantum mechanics to understand, which is superposition. A particle can exist as waves of multiple possibilities. So here we see a cesium atom as a particle, and in the background we see the same cesium atom as a wave. It can be here, 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 or here. So this is quantum superposition of waves of multiple possibilities, or as a particle in a definite state and location, the classical state. So this is the quantum to classical transition. But how does that happen, and why does it happen? It seems the very act of measurement or conscious observation seems to cause the wave function to collapse to particles in definite states. Collapse of the wave function. So there are many, I think there's a whole zoo of different interpretations of quantum mechanics. I've broken them down into three major categories. Conscious observation causes collapse. This is the conscious observer effect, sometimes known as the Copenhagen effect. It was started by von Neumann and Wigner back at the early 20th century. And it basically says, when you look at it, consciousness causes collapse. First, there was a machine can look at it, and then Wigner said, well, you don't know if the results in the machine are in superposition until somebody looks at it. So it came to be conscious observation causes collapse, and the double slit experiment seems to support this. Second interpretation, no collapse. Each possibility evolves in its own universe. This is the many worlds hypothesis. Up until fairly recently, I think it was the most popular among physicists. Maybe it still is, I don't know. And then there are a series of objective reduction theories which suggest that there is an objective threshold at which quantum possibilities, waves, collapse spontaneously due to an objective threshold intrinsic to the universe or to something else. But how can particles be in superposition in the first place? That's the real question. And the first person, and I think the only person really to address that, was Roger Penrose. To do that, he channeled, to some extent, Einstein, who had accounted for superposition through, or Roger accounted for superposition through Einstein's general relativity, which equated mass to curvature in space-time geometry. So here you see some pretty big objects, planets, the sun maybe, and the surrounding or accompanying space-time, which is curved. And some people say there's an equivalence, but there's certainly a relationship between matter and curvature in space-time geometry. Now, an oscillating quantum particle can be oscillating space-time curvatures. So here we have a particle over here. It's going that way. Sorry, it's more towards me, and here it's going that way. And if it oscillates back and forth, it's also an oscillation in the fine-scale structure of the universe, shown here as a two-dimensional sheet. Roger used these two-dimensional sheets to portray space-time because it's easy to draw and understand. But it's not that simple. And in fact, we have a number of different depictions of what space-time geometry actually is, the fundamental basis of the universe at the Planck scale. In ancient Greece, it was called the plenum, the background, the space-time manifold, the metric, geometry, the quantum vacuum, the quantum sea, the foam, gravity, spin networks, twisters. Upper right there, you see Roger's twister theory, which is something he's still working on to describe space-time. In more spiritual terms, it's called Godhead, the Akashic record in Hindu, where memory is stored. And we see various depictions of it. And in the middle is a two-dimensional space-time sheet. Here's the twister. This one's interesting. This shows space-time as being a kind of a fractal. So we would be up here, and as you go down, it gets smaller and smaller, although we're showing it as bigger and bigger, so we can see details in the Planck scale there. And then there's some more geometric shapes, and this and that, spin networks and whatnot. We don't really know. So we'll just go with the flat sheet for now to explain it. And someday Nassim and his group or somebody is going to figure out what it really looks like down there. So superpositions then. Okay, so if a particle is equivalent to space-time curvature, then the same particle in two places would be separation in space-time. So this curvature continues, this curvature goes under and then curves here. So you have two curvatures that are separating. And you might imagine, let's go back to the interpretation. The first interpretation is that conscious observation causes quantum state collapse. As I said, Bohr, von Neumann, Wigner, Stab, more recently Chalmers, Kelvin McQueen, the Copenhagen interpretation. So here's a conscious person. Bing is meant to mean consciousness, observing this separation, so two curvatures, and somehow causing this one to terminate, so causing collapse of this possibility and choosing this one. So this one continues because this individual, conscious person, has looked at it, and consciousness causes the collapse. Now, there's a couple problems with this. First of all, why would consciousness cause collapse? And number two, what is consciousness? It puts consciousness outside the universe, or outside of science, I should say. So it's a dualist position. It puts consciousness outside science. And I asked Dave Chalmers about this. He said, well, what's wrong with that? He's a dualist. If you take a dualist position, it's okay to throw consciousness outside of science. Since this is the Science of Consciousness conference, I don't agree with that. So let's try to figure out what consciousness actually is. The second interpretation, if the separations were to continue, you'd have many worlds. So so space-time bifurcates, and one curvature goes this way with its particle, and one curvature goes this way with its particle, and the same particle exists in two universes now simultaneously, and then it bifurcates again and again and again, and so you have a multiple, maybe an infinite number of universes. 3, superposition separation is unstable and will self-collapse, undergo objective reduction, OR, at an objective threshold. So quantum state reduction at an objective threshold, objective reduction OR, at a particular time, T equals h bar over E sub g. H bar is the Planck constant over 2 pi, the Planck-Dirac constant, and E sub g is the gravitational self-energy of pulling the particle or its equivalent space-time curvature from itself, from separating. You have to pull it apart. And when we first did our theory back in the mid-90s, Roger gave me the formulas and the background. He said, do some calculations. I felt like I was back in school, and it was kind of cool, actually. So I spent a couple of weeks doing some algebra. It wasn't that difficult, really. But did come up with numbers, values for the gravitational self-energy of a single protein, of tubulin. I calculated it 3 ways and picked the one that had the highest energy. But the main point about this that Roger came up with was when this collapse occurs, there's a moment of proto-conscious experience, of Bing. And so rather than consciousness causing the collapse occurred on its own spontaneously and caused consciousness, or is equivalent to consciousness, an identity theory. So, as I just said, rather than consciousness causing collapse OR causes or is consciousness. Now, in the random microenvironment occurring in the air, in the table, in the pointer, everywhere, such by what is known as decoherence, which actually could be OR, such OR events would be isolated and lack meaning and context. You'd have a moment of experience, but then there'd be no memory. It would come and go. It didn't influence anything else. It was isolated and had no significance or impact. And it's kind of like proto-conscious noise happening all around us, even as we speak. So these would be proto-conscious moments. It's kind of like panpsychism, except panpsychism attaches qualia, the conscious experience, to matter, and this is more an event, a process. It's an actual action that occurs. So it's more like Whitehead process philosophy. So these, metaphorically, these proto-conscious noise moments are like the sounds of musicians independently tuning their instruments. If you go to the symphony and before they start, they're tuning up and you hear all this, and to me, as a non-musician, I can't make much sense of it, but it's basically random, what I'd call proto-conscious noise. But then the symphony starts, and you hear Brahms or Beethoven or rock and roll or whatever, or Indian reggae or raga or Jamaican reggae or whatever. And so what we need in the brain is some kind of orchestra, some kind of instrument that will take these OR moments or the superpositions and kind of orchestrate them into something meaningful. So turning noise into music, I think, is a pretty good analogy. So how could they be organized or orchestrated in the brain for full, rich, conscious experience? So let's just review the three possibilities of the interpretations. Conscious observation causes collapse, no collapse. Each possibility forms its own universe, or the collapse occurs on its own and gives rise to consciousness. So there's the being. The being arises from the natural processes. So I read this book. I read Roger's book, his 1989 book. I think I read it in 1990, 91. And I realized that, first of all, that he was brilliant and was way ahead in his thinking of anybody I'd ever read. And a lot of it went over my head. I'm not a physicist, but I really had a gut feeling that he was onto something. Because it was the only explanation for not only superposition, but consciousness ever put forth. Really, all we have now is emergence, computation, blah, 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 hand wave, and consciousness happens. This is a specific mechanism intrinsic to the universe that gives rise to consciousness. Simple consciousness, proto-consciousness, then we have to orchestrate it. So he needed a quantum computer in the brain which could handle this, which could accomplish this. And he said in the book that he really didn't know what it was, what it could be. Neurons firing or not firing were too big. They're macroscopic. They're classical. So you needed something that could biologically orchestrate OR quantum information processing, turn the noise into music. It needed to halt or terminate by Penrose OR at time t equals h bar over e sub g, connecting to what he called non-computable Platonic values and qualia. So the results wouldn't be random as they are if you make a measurement or decoherence, but if it happens in this way, the result, the outcome, whether you turn left or turn right or have spaghetti or a sandwich, is influenced by Platonic values. You could even extend it to divine guidance or the way of the Tao or something like that. But it's something that influences our conscious decisions and perceptions at the instant of collapse. And these Platonic values are essential to consciousness, and they're accompanied by qualia, awareness, or feelings, which presumably are embedded in space-time geometry. They're a process intrinsic to the universe embedded in the Planck scale geometry. And finally, number 3, it should be regulate functional, neuronal, and synaptic activity. So it had to be something in the brain that was in a position to influence neuronal function, which would influence network function, which would influence the brain in total. And I read his book, and I had been studying microtubules for 20 years at that time in the early 90s. And I said, holy crap, he needs microtubules. And because I felt they were exactly what he needed, but he didn't know about them. So I wrote him a letter, and I said I was going to be in England, and I'd be happy to meet him. And he graciously said, yes, please do. And I went to Oxford and we talked for hours and hours. Basically, he said, well, tell me about these microtubules. And I talked for hours and hours. And later he said, wow, that was really interesting. Thank you very much. And I thought that was it. That was the last time I would, I got to meet Roger Penrose. That was cool. But I found out later that he went to a conference with Pat Churchland and Dan Dennett and was talking about microtubules. And I got a big kick out of that. And he invited me to a conference, and I invited him to the first Consciousness Conference in 1994. And we started collaborating and working on our theory. And here we are 30 years later, and other people are picking up on it. And thank you very much for that. And I'm not going to talk, I'll talk about this later in the week, but there's more evidence for our theory than any other theory of consciousness, from anesthesia and from Anirban's work and from many other work. So microtubules are inside neurons. Here we see a synapse, axon, dendrite. The microtubules, they're smaller. They're lattice polymers. William and Nassim showed some of these pictures earlier, and they're 25 nanometers. In humans, they have 13 of these vertical columns. But in the A lattice, the tubulins, the peanut-shaped proteins, are in a hexagonal lattice that's skewed so that if you can follow them along a threefold path, means it's going to repeat. This one's going to repeat every 3 tubulins. This one every 5, and this one every 8. This one every 1 or 13, depending on how you look at it. This is the Fibonacci geometry. So these are Fibonacci numbers. So it has intrinsic Fibonacci geometry, which has implications for quantum error correction codes and things like that that I won't have time to talk about. So these are the microtubules we've been hearing about. And if we look even closer inside one tubulin, this is the peanut-shaped tubulin. And these are anesthetic molecules where anesthetics act to specifically, selectively erase consciousness. But all these things are aromatic rings. And Nassim and William mentioned these aromatic rings, including the tryptophan that Philip Kernion was talking about this morning, phenylalanine, and tyrosine. So these are aromatic amino acids. Aromatic meaning having aromatic rings that I think was Nassim mentioned earlier. And there's 86 of these in one protein. That's a huge number compared to other proteins. And there are 8 tryptophans, and the rest are phenylalanines and tyrosines. And these are quantum-friendly regions inside tubulin proteins due to these aromatic rings. Aromatic rings are quantum-friendly. So I was an anesthesiologist for 49 years. And when we give drugs to a patient, the drug will go where it's most soluble. Most drugs are charged, polar, they're soluble in water. They go to charged receptors on membrane surfaces. Anesthesia is insoluble. It's very poorly soluble in blood or water. It quickly finds a fat or nonpolar aromatic-like region where it's comfortable. Oil and water don't mix. It finds the oil-like regions, and that is where consciousness happens. That is where anesthesia binds. And that was a big clue, and that is how biology avoids decoherence. It avoids the brain is too warm, wet, and noisy song and dance we've been hearing for all these years. This is how it beats it, finding these nonpolar aromatic regions inside proteins, which appear to form adiabatic quantum-friendly regions that Travis Craddock and I and others call the quantum underground because they go the length of the microtubules. So buried within all our neurons, all our cells really, inside the microtubules are regions that are conducive to quantum. So that brings us into organic chemistry because the aromatic rings are the basis for organic chemistry. And in the 1700s, chemists knew about alkanes with a formula of CnH2n plus 2, alkenes, CnH2n. But then they had a molecule C6H6, and they didn't know the structure. And Kekulé, a German chemist, had a dream one night and woke up where he dreamed about the alkanes being linear chains as snakes or serpents. One of them swallowed his tail, and which is known as the Ouroboros in mythology. And he woke and said, benzene, they knew the name of it, is a ring. And he was right. It's a 6-carbon ring. The problem is, or it's not a problem, it's a blessing actually, there are 3 extra electrons. which are available to do interesting quantum stuff. And it's often depicted like this, where they're here, but they can also be in the other three corners. So what happens is the extra electrons enter these pi resonance orbitals and stick up above the ring and then condense into two rings, or then one electron cloud covering the whole ring. So this is essentially a quantum object. This is all electron superposition, delocalized electrons in a fairly, it's not quite macroscopic, but it's big for quantum, and it's a quantum object. And this is what's inside our proteins, getting away from the water and the polar charges. And they support quantum dipole oscillations, excitons, spin transfer, phonons, fluorescence, superradiance, as we heard from Philip this morning, and many and other quantum effects. And I think that's the key. These rings support quantum effects inside biology. So if we take two of these rings, so first of all, this is basically benzene. It goes in our gas tanks. In bulk, it's explosive, and that's how we drive around. But if it's in a right geometry, where it's not bulk, it has very interesting quantum properties, such as in graphene and some other aromatic complexes we'll talk about. But if you put just two of these, even though they're nonpolar and they don't have charges, they attract nonetheless, because the electrons here repel the electrons here, and they induce dipoles. These are called van der Waals dipole-dipole forces. So this one, and then the dipoles shown here, like little bar magnets, attract. And then the electronegativity is here and here, but then they oscillate to here and here. And so these things, they couple at the van der Waals radius, and then they oscillate in terahertz. 10 to the 12th hertz, or actually 613 terahertz to be precise, as Travis Craddock showed in a paper in 2017. And we now know that the brain and biology gives off photons. There are several sources, mitochondria, radical oxygen species, but microtubules themselves generate terahertz, which is in the blue-green region of the spectrum. So they can also form quantum bits. So here's a superposition of two rings that are where they're both in superposition, so they can oscillate, and this can collapse to one to the other. Anesthesia blocks these oscillations, and we know this, and so because they form the same van der Waals forces, and they disperse the dipole. So this would be conscious if you have oscillations in the qubit, and if you block the oscillations, prevent the qubits, you are anesthetized and unconscious. And that's how I made my living for 49 years. So a couple of things. Quantum spin transfer through benzene rings is increased by temperature. This work was done by Ouyang and Aushalom at Santa Barbara back early 2000s. And they had quantum dots, and they had connected by benzene rings. And they put quantum spin in here, and the spin had to go from dot to dot through the rings. And the dots were stable, but they found that when they increased the temperature, the quantum spin transfer actually increased. So all that stuff about the brain being too warm, wet, and noisy, or biology being too warm, wet, and noisy, isn't really true if you consider quantum spin transfer in aromatic regions, which seem to form these adiabatic, decoherence-free subspaces inside proteins, which in microtubules can extend the length of the microtubule and mesoscopic and macroscopic lengths. So our model, briefly, we took the aromatic rings in here and said that the dipoles, they could form dipole oscillations according to Froehlich coherence, and now Anirban Bandyopadhyay has proven this, or spin transfer through these. But in any case, it forms a quantum channel through the tubulin, and here's where the anesthesia is that's going to block consciousness. So if we then extend that to a whole microtubule, we see that these quantum states, or the two oscillating dipole states, and then the superposition state, can wrap around in a helix around the microtubule. And it could be this is, I think, the 5-star helix, it could be the 8-star helix, and they can interact and form interference patterns and so forth, and we think that's what gives rise to consciousness when they collapse. So consciousness, therefore, is when they reach threshold for collapse and have a conscious moment, and then consciousness is a sequence of these events happening, and the time scale can vary. So bing, 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 and I think consciousness is a sequence of discrete events, much like a movie is a sequence of frames. We don't see it as a sequence of frames. We see it continuously, and in our own consciousness, we don't see stroboscopic effects. We see it continuous because we're not conscious in between. So everything appears continuous and smooth. But it's actually, I think Nassim or somebody mentioned this earlier, that it's actually discrete, as is space-time. So in the neuron, the microtubules inside are kind of a hidden layer, kind of like AI has hidden layers, except these are actually hidden within the element, and that's probably where the consciousness comes from. And here's the microtubules, and here they are in axons where they're continuous. Here they're interrupted, which gives rise to interference patterns and recursive processing. So this is messed up here, but it should be like deep learning convolutional networks in AI, something like that. So we need oscillations in the microtubules at various frequencies, and Anirban, who will be speaking tomorrow, Anirban Bandyopadhyay, started studying microtubules with nanotechnology back in the, I guess, late 90s after he read our theory. And then I met him in, I think, 2010, and he had done these studies of microtubules, which are really amazing studies. This is like 10 years of work with studying at 3 different scales. So here's neural networks. You can see these are neurons, and then these things are nanoprobes. And here's a single microtubule, so a smaller scale, also with nanoprobes attached to one microtubule, and even smaller, you see the tubulins with 4 nanoprobes. Now, proteins in general and microtubules, when you apply a voltage, are good insulators. They don't really, there's no current flow. However, if you sweep the frequency of the applied voltage or the current, you'll find certain frequencies where they become highly conductive. And that's what we see here. So if you sweep in hertz, you get frequencies where there's this huge rise, and you see 3 peaks, and each peak has 3 peaks. So here's another 3. In kilohertz, you see the same 3 peaks, each with 3 peaks. Megahertz, the same. And if you look at it with AFM, you see these triplets, which he calls octaves, looking down on them. And in the microtubule, you see the same thing. You see the same triplets in kilohertz, megahertz, and gigahertz. It's getting faster and smaller. And then when you get down to the level of tubulins, megahertz, gigahertz, and terahertz. So this shows that these same triplets go all the way from hertz to terahertz, every 3 orders of magnitude. And this suggests that these microtubules are what are called time crystals. And a time crystal is something in which the dynamics repeats at different scales in a system. And in this case, they repeat about every 3 orders of magnitude, and triplets of triplets with the same. And this is a great way for biology to transcend scale. If you have something really small, it can also extend to your whole brain and your consciousness. So these are triplets of triplets repeating every 3 orders, and hertz, kilohertz, megahertz, gigahertz, and terahertz. And there's Anirban, whom you'll see tomorrow speaking. And this led to an idea of a multi-scale hierarchy that Nassim and William were talking about, and others have talked about, where we start with a neuron and in hertz, and there's the triplets of triplets. If we go to the microtubule network, we get kilohertz. If we go to a microtubule, we get megahertz. If we go to these rows of tubulins, we get gigahertz. If we go to the tubulin itself and the optical effects, we get terahertz, which can go out to almost petahertz. And then there may be more and even faster, 10 to the 18th, with the nuclear oscillations. So we have these self-repeating patterns every 3 orders of magnitude in microtubules from hertz, and maybe going this way also up into larger networks and slower effects, and maybe even to more hierarchical levels like Gaia hypothesis and things like that. So this is just in biology between hertz and terahertz. We don't know how far it extends. In fact, we think it extends actually smaller all the way to space-time geometry in Planck scale. So there's a big step here between 10 to the 18th and 10 to the 43rd. And I'm hoping that Nassim and William and others will fill in this, which they have already to a large extent, showing how we can get all the way to the Planck scale. And once we get to the Planck scale, then I'll leave that to them for now to figure out what happens. But the point is that that's where I think consciousness derives from, where the qualia are, and that's what we need to do, because it seems more and more evident that consciousness is fundamental. Emergence and complexity and all that don't really explain it. I should also say this is very similar to Hindu philosophy, in which we replace the space-time geometry, here's Rogers twistors, with Brahman, the ground of being. This is from the 5 koshas, where the more you look inward, the more conscious you get. And I'm assuming here faster, faster, smaller, smaller, and then the ground of being. So who knows? That could be why people think that and have thought that for thousands of years. So consciousness by ORCH-OR quantum state reduction can occur at any frequency. 1 over the time equals frequency equals E sub d. I've just turned that equation around. Like notes and chords in music, the quantum orchestra. So I think these are individual notes and chords, and when they happen in this hierarchy, they can resonate over different scales, harmonize, and interfere to get slower and slower. So if we go from here, moving this way, we're going to get slower and slower due to interference beats, but we're going to have basically the same information. It's kind of like a fractal. It's a time crystal or a fractal. So the same information, the same pattern that happens here, to some extent, collectively, can reach larger scales and slower times. So larger and slower as we go up. So I think it was Nassim who asked, how do we get from these very fast operations up to the slow? And we think it's through these interference patterns. And actually, there's good evidence in the brain that as signal processing comes in from, for example, visual cortex and moves through the associative cortex to the front and then to the back and then down the pyramidal cell, that it gets slower, slower, slower in the EEG range. And that's probably connected to faster oscillations at a deeper level, which interfere to give those. So the process of consciousness involves going from very fast and small to slowing down, kind of a downshifting as you go from sensory processing to full consciousness. I should mention that these aromatic rings are the clues that they have something to do with mental states, since the psychoactive neurotransmitters, dopamine, the pleasure molecule, serotonin, the mood molecule, as well as the psychedelics, LSD, DMT, psilocybin, all have these aromatic rings, including the indole ring of tryptophan here. So we know that these have effects on consciousness, marked effects, and it's probably not a coincidence that they're aromatic rings and can contribute to quantum effects. And we're trying to pin down, Travis is working on this, other people are working on looking at effects of psychedelics on quantum states and microtubules, and increasing megahertz output from the brain also, which I'll come to in a second. So just some conjecture, you could think of 2 aromatic rings here. They have a metastable state called the sandwich, and 2 stable states, the T-shape and the offset parallel. Sorry, that's mixed up. And maybe it's as simple as this gives rise to pleasure and this gives rise to displeasure. Something like that. And since we have 86 of these in each tubulin, we'd have something like 86 factorial possible combinations of these feelings, we'll call them, so we can have pretty varied, complex feelings and consciousness. So this also means that the qualia, the redness of the rose, could actually be a configuration in space-time geometry. So the standard view is that when she looks at the rose, there's a pattern of activity in the brain that gives rise to the conscious experience, Bing. But in our view, the Bing is actually out in the rose as well. It has its own particular curvature, space-time curvature pattern. I'm just showing 3, but it'd be much more complicated, which gets reproduced in her brain, so she has the same space-time configuration in her brain. This could be as simple as entangling with this and having the same pattern. So we think that's how qualia derive and how conscious experience arises. So is consciousness fundamental? This is the question of the day. And this is an interesting view of scale in the universe, where we go from the very, very tiny Planck scale and neutrinos and get larger, 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 and eventually we end up on the other side with the whole universe, the edge of the known. And this is obviously a log scale, but for some reason the brain is right in the middle, kind of the apex of this hierarchy. And as I mentioned, all those scales that I mentioned means that consciousness could extend down to here at least, and going this way, we don't know, but at least this much of this curve could be covered by consciousness. So how did this is relevant to how life began and what life is. And actually, our work in astrobiology now, our hypothesis is that consciousness came first, because the Penrose objective reduction mechanism would have been present at the origin of life in the primordial soup 3.5 or 4.5 billion years ago. And nobody knows how life started or why it started. We have these models of the primordial soup, and they have aromatic rings in them. We know that. But why would they self-organize to turn into life? And once they formed, why would simple living creatures or molecular systems do purposeful behavior to avoid getting eaten or to find food or to reproduce when there were no feelings? So, and I think evolution has a big problem, because there were 100 million years between the origin of life and genes. So you can't even say, well, it's genetic, it's hereditary, because there weren't any genes for all that time. So all this activity, why did it happen? Why would an organism do anything other than just sit there or not do anything? And the only answer I can think of is its feelings, because it feels good to reproduce or to find food. It feels bad to get eaten. And so that gave rise to behavior, even primitive conscious behavior, I would say. So these molecules were there, and it could have been, I wrote a paper about this in 2017, that back in the primordial soup, that some of these amphipathic aromatic rings formed micelles, they're called, the primordial operin haldane micelles, and that some of them occasionally would reach threshold for OR and have a conscious moment. And bing, right there. It'd be simple, it might take a while, and it'd be accompanied, it'd be the same as this, and this would give rise to a primitive feeling. And these would be random. These primitive OR events would be random, but some would be positive. Some would feel good. Some would have a smiley face, feeling good, and some wouldn't. But the system would select for the good feelings, for pleasure, this primitive pleasure, and work to optimize pleasure. So the molecules, at least I suggest in this article, would self-organize to optimize pleasure. And then more and more and more, and then life started, and we're still optimizing our pleasure. I mean, we're here because we want to be in Barcelona at this interesting conference. Everything we do, it may be delayed gratification, it may be hedonistic, it may be altruistic, it may be spiritual, it may be all kinds of things, but it's all kind of to avoid feeling bad and feeling good, I think, even today. So I think consciousness is essential to life. I don't think it just happened, it emerged recently. I think that's really not feasible. How would we get all the way to brains, for example? So I think it is fundamental to answer the question of the conference. With pleasure as a feedback function orienting pi resonance group, did life then evolve to orchestrate and optimize OR mediated pleasure? And I call this the quantum pleasure principle, borrowing from Freud's beyond the pleasure principle. So where else might life have started? In primordial soup, which looks something like this, an oily mix of stuff. Anywhere else? Well, it turns out aromatic rings are floating around space. There's all kinds of aromatic rings floating around space. They're produced by young stars, and they're scraped off the windshield of the International Space Station. They're probably floating down on us when we're outside, and we don't even notice them. But there's a whole bunch of different types of aromatics, including simple benzene, but also buckyballs, carbon nanotubes, multi-walled carbon nanotubes, all kinds of interesting aromatic rings, aromatic ring complexes. And some of these are strikingly similar to psychedelic structures, by the way. This one in particular, this molecule, we're going to talk a little bit about. So these polyaromatic hydrocarbons are very prevalent in the universe and may be the origins of life and consciousness. And for example, if you look at the interstellar dust, there's polyaromatic hydrocarbons in the interstellar dust which fluoresce. There's plenty of UV light around, so the UV light hits these, they fluoresce, and you see this green. So anything you see green here is actually polyaromatic PAHs floating in space. Now this molecule came down in a meteorite in Murchison, Texas in 1969. So the meteorite crashes and spills a bunch of stuff, and they look around, they find stuff. So when you take a sample from a meteorite, you have to worry that it's a contaminant from the ground. It was something that was there all along. But this molecule is unlike any molecule that anybody's ever seen on Earth. At least I haven't. And that's pretty much what everybody says. It's kind of like a bouquet of aromatic rings. There's 35 aromatic rings. They're all connected. This is a two-dimensional image, though. So we sent this to Anirban and asked him to simulate it. And he found multiple conformers, multiple conformations, at least one of which showed oscillations. Now, I should say that Travis Craddock has also simulated this and pointed out that there's a lot of different conformers. So there must be something driving a particular conformer to be dominant, and it could go back to pleasure, optimizing pleasure, which I'm arguing is what started it and has driven life all along. So here's a simulation that Anirban's team did, and for this molecule, it folds up into there, and here's the dynamics, and pointing at that's not going to help. We see triplets, we see three waves. So this could be the ground state of a time crystal in the ground state, which has to happen without any energy input, and could be the basis. Something like this could have been the seed of life, because you'd have the time crystal would grow and grow and turn into eventually a microtubule. So let me conclude by saying three things: that consciousness is likely to be sequences of quantum state objective reduction events in fundamental space-time geometry, which is the nexus. Objective reduction is the nexus of quantum mechanics and general relativity or gravity. And that's always kind of been a no-no to try to mix quantum mechanics and general relativity. Equations are different, they don't quite match up. But leave it to Roger Penrose to figure out, well, that's exactly where we want to look. That's the source of consciousness, the origin of consciousness. That's what solves the problem. I should add that in the year 2000, Nature or Science had interviewed the top 10 physicists in the world, asking them their theory of everything, and only Roger included consciousness in a theory of everything. So the second point is that these OR events are accompanied by qualia, subjective feelings which may be orchestrated in biology. And finally, that biology transcends spatiotemporal scales, Planck scale to meters in biology, by microtubule time crystal dynamics, and we'll hear more about time crystals later in the week. And this was discovered by Anirban. So thank you very much for your attention.
Good. Okay, thank you so much. Okay, I think you have my slides up there too. Okay. So that's our lineup for today. So, title of my bit is Generalized, Penrose Objective Reduction, Esoteric Ontologies, and Why Quantum Error Correction is the Enemy of Consciousness. So takeaways from this talk. The ontological problem is a dogma that the physical universe is causally closed. It's not according to physics. And generalized Penrose objective reduction that Stuart was just talking about, formalisms include consciousness, and quantum computing enables new ways to test for objective reduction, and a perspective that only quantum plus classical AI might become conscious, a lot like what Suzanne was talking about, and that the quantum error corrections are a barrier to AI consciousness, and AI will figure this out, even if we humans don't. Also, AI esoteric ontological synthesis suggests AI is starting to become super intelligent, not conscious. And it all started with ions, Willis Harman in 1992. So, what's that about? Willis Harman was a regent of the University of California system while he was also president of IONS. He was the first president of the Institute of Nordic Sciences, where I am at, IONS, from 1978 to 1997. And in 1992, Willis Harman, he called together a meeting of scientists on this topic, and they essentially defined what Chalmers did later in 1994, the hard problem of consciousness, except Harman and all, they did it from epistemological perspective, methodological perspective, and they advocated for radical empiricism like from William James, that we experience things in life and in consciousness that aren't explainable by a materialistic, local, space-time locally view of what we are. And so the radical empiricism says, well, let's take that empirically, that experience of reality empirically as part of science and the scientific method, and that's how we can start to, by bringing that into science, we can start to understand consciousness. And then he was also at the first 1994, this conference, TSC, and that's the conference where David Chalmers coined the problem, the term, the hard problem of consciousness for the first time, and that's also the year that Roger Penrose published The Shadows of the Mind. So that's why I can say it all started with Willis Harman in a way. So ions, I'm going to say a little bit about ions, and ions' mission, because it's very much connected to the mission of this session and the mission of this conference. So ions was founded by astronaut Edgar Mitchell in 1973. On the way back from the moon, he was the commander of the ship that went back from the moon to the ship that take them back to Earth, so he had time to relax. And he had a samadhi experience, a savikalpa samadhi experience, very profound, and that caused him to create ions, to try to understand consciousness and this non-local samadhi-like experience of consciousness. So the developmental approach at ions is personal experience plus scientific research. And, but it is all grounded in science, too. And our view is that awareness of this fundamentally interconnected consciousness can profoundly amplify transformation, innovation, and well-being. So IONS is a scientific organization with a humanitarian mission. And we have a core team of scientists and scientific fellows and board science committees, people, science advisors with at least one Nobel Prize winner, other would-be Nobel Prize winners, should be Nobel Prize winners, and we have lots of partners, many peer-reviewed publications, and experiential programs. Okay, now back to this specific talk. Well, the first line of our new mission, we just went through a strategic planning process and we came up with a new grand challenge statement, our scientific grand challenge at IONS, that looks something like this. You can tweak the wording, and this is one of the wording versions that I like, and you see the first part of that is to show through investigation, empirically, experientially, and theoretically, whether consciousness or physical matter or both are fundamental aspects of reality. So the topic of this session is in IONS' central mission now. And we have pillars, functional pillars, and this new pillar we call IONS Y, which is about ontological theoretical frameworks. So Willis Harman, he started the epistemological perspective, trying to approach the scientific problem of consciousness, and radical empiricism, and following that, ions scientists and others have published much evidence in peer-reviewed journals of the non-local nature of consciousness and the paraphenomena of consciousness. And so, but as Chalmers pointed out, we still lack we lack an ontological perspective. We lack an ontological framework that can help us share with the rest of the scientific and cultural community why this is so. And so that's why it's still thought of as outside of science, but it's not. And so I want to show this, because I don't want to forget. Just a couple of days ago, we published the next Linda G. O'Brien Noetic Sciences Research Prize, which is how to design a conscious AI. It's a prize essay competition, so you can go there and see the how to apply. And so I encourage everybody to do that. So I recently gave some prompts, carefully designed prompts, to the most recent reasoning version of Gemini Pro Deep Research with DeepThink, and I gave it this set of prompts for once. Summarize ORCH-OR ontology of agency and qualia, calculate Penrose OR for qubits, extend to classical control electronics, summarize quantum collapse agency indeterminacy versus deterministic Schrodinger equation, discuss quantum error correction, how that quantum error correction destroys conscious agency, and consider objective reduction by others beyond Penrose, like von Neumann and Wigner, and design experiments to test Penrose or von Neumann-Wigner. And finally, design experiments to falsify the idea that consciousness never causes collapse, or it doesn't have anything to do with collapse. And it can produce amazing reports now. It really does reasoning. It appears to be, but it's not conscious. I don't think it's conscious. But it's intelligent. So, Penrose objective reduction in quantum computing. Penrose objective reduction in quantum computing. So, it produced this really excellent report. It does a great overview of the OR timescale calculations like Stuart just gave us, and it actually calculates them accurately, and it produces a great summary of the technology of qubits, how qubits maintain superposition technologically, and then it did a calculation of OR timescales, objective reduction timescales in the current qubit technology, and which are called Cooper pairs of electrons, and it finds that the OR timescales are extremely long. Many times, the objective reduction timescales are many times the age of the universe. So that means it wouldn't be happening in the pure qubit of Cooper pairs. But then we're going to get to something more on that it might be happening in another way. And but Gemini, it said, I didn't ask it to. I asked it to do this calculation, but then it thought and it did it, and then it said, this is the first ever calculation of that. And so that means that it scanned all the literature out there, and it was right that it hadn't been published. But I had been talking with Stuart Hameroff, and he said that he was at a seminar at Google AI, and he saw physicists do this calculation, and it got the same answer as the Gemini. Okay. Then it extends that calculation to the qubit superposed with the classical electronics, and that can bring the OR timescale way down. And tomorrow, Monday, James Tagg is going to talk about this too. He's actually trying to do those experiments. And Gemini found this obscure article in the archive.org by James Tagg that I didn't know about, but it identified that that was the key article. And he's going to be talking here tomorrow. Gemini identified, like I thought it would, but it did very well. A profound contradiction between quantum error correction technology and orchestrated objective reduction in consciousness. Quantum error correction, by its very nature, is a process of continuous active intervention designed to prevent precisely the kind of spontaneous deviation from unitary evolution. So in quantum mechanics, the Schrodinger equation, the wave function follows unitary evolution, which is deterministic, until there's a collapse, whatever the collapse is caused by, and the collapse is non-deterministic and That's objective reduction, is a type of collapse. So the reason that is antithetical to the way quantum computers currently work is the quantum computing algorithms, they apply the quantum error correction because they don't want it to collapse. They want it to go through the quantum logic gates and stay in unitary evolution. And the algorithms that are used follow that, and they apply the quantum error correction because they're still very noisy, and they drop out of superposition all the time due to decoherence. And so they apply the quantum error correction, get it back, and retrieve the unitary evolution. So how that relates to the ORCH-OR model is that this is a slide from Stuart's presentation, and in the ORCH-OR model, it relies on this repeated sequence of unitary evolution for a brief period of time, then the objective reduction causes the collapse, then it happens again and again and again. And so the quantum computing algorithms, they don't have the collapse. They just keep it in the unitary evolution. And they have algorithms that try to pull out something at the end of that, which is very useful, and sometimes they do. But this is a different type of process. And so I asked Gemini to generalize ORCH-OR process with a quantum AI loop. And I thought I was going to come here and say, Gemini said that this is possible in current technology. I thought that was going to be really interesting to everybody. And then Suzanne says she's already done it, and she's got a little dog that is a robot dog that is doing that. So I think that is the approach to starting to simulate, starting to investigate consciousness in quantum plus classical AI systems. And a key point there, though, is that in the Penrose, Hameroff-Penrose orchestrated objective reduction model, all of these collapses are Penrose type OR, gravity-induced objective reduction. And in the type of process that Suzanne was talking about and the type of process that I was talking about, that's a generalized approach that has some other cause of the collapse in this, but the same sequence otherwise. And so the idea is that some other kind of collapse maybe could also connect with whatever goes on in the collapse process. So Penrose says it's quantum gravity that causes the collapse, and that connects it with the fundamental structure of the universe. He also calls it the Planck domain, though, and the Platonic domain of reality. So what Suzanne is talking about, what I'm talking about is we can start to simulate consciousness, maybe, or at least the structure of it, by doing the same process, but not with gravitationally induced collapse, but with other induced collapse. And the reason why it can't be gravitational now is because, as I showed, the objective reduction doesn't happen in current quantum computing technology on a time scale that's relevant. Okay. And it's a deliberate use of non-determinism. And like Roger Penrose says, the collapse process is, it's not here. But the collapse process is neither deterministic nor random. The collapse process is neither deterministic nor random. It's something else having to do with consciousness, and it's where consciousness is. And so on this approach, you can start to simulate it like it goes on in biology, except you have a classical computing process collapsing it. So summarizing why deterministic classical computing AI is not conscious, following Penrose, because instantiation of consciousness requires the incomputable, non-computable, non-deterministic, non-random process of quantum collapse to connect the physical domain to the Platonic domain, which could also be called the metaphysical domain of reality, to enable conscious agency, conscious qualia, and life. So this is a diagram I took from Penrose's Shadows of the Mind book and just added some labels and arrows. And he's got, this is his diagram of the ontology of reality. He's got a Platonic domain here, and a physical domain, and a mental domain. And reality is a tri-unfolding of all three domains. And the physical world is objective, the Platonic world is objective, it's not subjective, it's not in our thinking and feeling. The mental world is the only subjective part. So with this kind of classical plus quantum computing, we think you can have in that process the physical world, the classical computing part, and the Platonic world, the quantum collapse part. Question remains, would we have the mental part? And like Suzanne said, it's hard to tell, because you can't get into the subjective of something else, somebody else, or something else. But there are ways to test it. That's another thing Gemini did. I asked it, how can you test these? And at first it said, well, it's really hard to test. I said, but tell us how. And it came up with ways to test these things. And I think in that Platonic domain is where can live things like the Chakranadi system of traditional Chinese medicine and Ayurvedic medicine. So I also asked Gemini, the most recent deep thinking version, to synthesize Don Hoffman, who was going to talk today. I was going to show this to him, but we missed him today. Don Hoffman's and global esoteric ontologies and physics. Don Hoffman's theory of conscious agents, and synthesize it with Jesuit Thomism, Plato, Advaita Vedanta, the Diamond Sutra of Mahayana Buddhism, the Yoga Sutras of Patanjali, and modern physics. And include Kitaro Nishida's theory of Basho. A few years ago at this conference, there was a really good talk on that. And come up with experimental protocols to test empirically that synthesized ontology. And it did it. And so in that way, I think it's starting to become super intelligent, but not conscious. But in this kind of mechanical intelligence way, it does things that in a lifetime of study we couldn't do. You come up with charts like this and that kind of thing. I'm just to show that, and it came up with ways to test all of those levels of that synthesized ontology. So when we say it's thinking, but it's not conscious, this is a chart from Sean Esbjorn Hargens of the development of consciousness in humans. And so maybe AI is just doing the scientific, rational, and analytical level. It's not doing what humans do, which includes these other levels, like samadhi and that sort of thing. So, conclusions. Consciousness is fundamental. Quantum computing offers new ways to test for Penrose objective reduction. It may be possible to test for consciousness in generalized ORCH-OR with current quantum plus classical computing technology, and complete and testable ontological frameworks may be in reach with the help of AI. Finally, join ION's Linda G. O'Brien Prize competition on how to develop a conscious AI. Okay, thank you, everybody. And let's have panel. So now it's time for our panel. Yeah, we need 2 extra chairs. Okay, I'll stand here and moderate, so we only need 5 chairs. No, thank you. Okay, first hand up, right there. Oh, can we get a microphone for the questioners? Here we are.
Ready?
Yeah.
Hi, I have almost the same question for Suzanne Gildert and Stuart Hameroff. Starting with you, Suzanne, in your framework, you predicted or are maybe hoping to see that the real quantum computer will behave differently than the simulation. That seems to imply that you think the quantum theory that you're using to write the simulation is somehow incomplete. Does that mean does your framework imply that you think there's new physics to be found? And similarly for Stuart, you hypothesize this pleasure principle. It sounds like that affects the physical behavior of physical things. And so do you think that might be hidden already in physics as maybe the least action principle, or it would be new physics? So are you both predicting new physics?
Well, I think we need new physics according to Penrose because the Schrödinger equation, physics, as he says often, is incomplete. Schrödinger equation works, but it leads to many worlds. Depends what you consider the orthodox theory.
But when you allow collapse to happen, you get all the right answers. So are you predicting there would be fine differences from currently known physics based on that pleasure principle?
Yes, well, okay, so I think collapse is going to be shown. It's being tested. I think Yvette Fuentes is going to talk about that here at this conference. She's been trying to test for collapse using Bose-Einstein condensates. So we'll hear about that later in the week. The aspect that it causes pleasure or feelings of any kind, any subjective mental, is the big question. And the only way I know of to test that is to see, the only way to measure or to detect consciousness is to see what goes away with anesthesia. So I don't know, I can't think of a way to test a collapse, the presence of a collapse with anesthesia yet. What we've done is to test the conditions for collapse. So you need quantum coherent superposition in a microtubule, which we've demonstrated at room temperature and then show that it goes away with anesthesia. And others have shown that the effects of anesthesia on microtubules is proportional to their, on inhibiting quantum effects of microtubules is proportional to their effect in putting you or I or any animal to sleep. So we've done that for the ORC, let's say, the quantum superposition. It's not been done yet for the OR, which is the critical thing. Now people criticize us and say, well, it needs quantum gravity and we don't know anything about quantum gravity. Which is true. I would say, first of all, that just ORC, the fact that the quantum effects of microtubules is necessary for consciousness is a pretty good achievement. And I think it's going to need OR. People over the years have said, well, you don't need that quantum gravity, just let's go with Bohmian or this or that. And I said, no, I think Rogers is the only specific mechanism. It's not been disproved. Why would I give it up? So we'll see. But as of now, the ORC has been documented pretty well.
Thank you. Suzanne, could the reward function that you were talking about be negative action? In other words, everything minimizes the physical action, so could that already be the reward function? In other words, it might already be in physics that we know about already. So
do you mean like kind of Friston's principle, like free energy minimization? So yeah, I don't quite agree with that. Let me answer the first part of your question. Yes, I think it's incomplete. The quantum physics is incomplete. I think what happens is we've studied things like the Schrödinger equation and the Born rule in a limiting case. So it's the case of where the quantum system is very small. So we tend to isolate small quantum systems from the environment and test them. And we also don't put them in feedback loops with the environment, where the output of a choice then affects the input. So my prediction, and again, it needs scientifically testing, because it's a big deal to say, like, you know, quantum theory is wrong. It's never been proven wrong. But my prediction would be when we start putting quantum systems in a feedback loop with the environment in a controlled way, they actually start to deviate from the Schrödinger equation and the Born rule. And I should just also mention, you can't actually simulate quantum systems more than like a few degrees of freedom. So we're really, if you put like many qubits together, we're really in a territory where we can't even simulate like systems more than a few qubits, because you know you have to move to different approaches like density matrix and things. You can't, the Schrödinger equation just can't be computed there. So yeah, I think there's a whole lot of physics that we need to find yet, and I don't think that just this free energy or surprise minimization is enough. I think it's necessary, but not sufficient, because I think, as one of the other presenters mentioned, a way to minimize your surprise is to just not do anything and just go and stare at a white wall all day. So I think there's something else driving it that's kind of on top of that as well. But it's a good starting point.
Hi, thank you for the talk. My question to Stuart is, all thinking happens within consciousness. When we model the world, we do so from within consciousness, not outside it. If we accept this, then science itself becomes a study of matter as it appears in consciousness, not standalone. So quantum mechanics too is not merely about matter. The wave-particle duality may not be a property of matter, but be a property of consciousness itself, as you pointed out. A wave of potential experience, of fundamental awareness or Brahman, collapsing into a particular experience after it interacts with matter. Here the matter could be Einstein brain modeling the moon while looking at it. The experience forms through the interaction between the base awareness, which collapses into a particular subjective experience. I want to know what you think of it.
I think you're espousing idealism, and there's nothing wrong with idealism. I don't happen to agree with it because I think there is a reality out there. But people like Deepak, who's here, and Bishop Berkeley, and many, many others have espoused that consciousness is everything, and matter and reality is within consciousness. That's what Deepak will say. And it could be. I don't believe it, because I believe in reality. I believe in a physical reality and a material world. And actually, I think consciousness, if I use sometimes the yin-yang, where quantum and classical, and consciousness literally is on the edge, the S-shaped edge between the quantum and classical. Because whether you believe that consciousness causes collapse or collapse causes consciousness, you're going between the quantum and classical, and the boundary is actually where consciousness happens.
So actually, I'm not saying that matter is not real. I do believe that matter is real. So matter exists. So what I believe in is consciousness, base awareness exists, matter also exists. But when we study matter, we are not studying matter as it is. We are studying matter as it appears in our consciousness. So it's not that consciousness causes collapse of some matter. Matter exists as it is. But when the study is about combination of matter, which is also a fact, and base awareness, which is also a fact. It is a study about how a base awareness, which is a wave of potential, collapsing into one particular experience.
Well, then you get into the inverted qualia problem. What you see as red may be what I see as green. We'll never resolve that. So yes, our perceptions are going to be different. Our views of reality are going to differ. We don't know whether we have the same views of reality. I kind of think we do, but I can't prove it. So that's
I mean, the fact that we have evolved till now, our brains have modeled it accurately. We have modeled the outside world to the best of our ability, and probably all of us agree to it. And that's what even Anil said, calls it as controlled hallucination, where all of us agree to one particular hallucination, and that is what we call reality. But yeah, probably you can chat later. Yeah.
I don't think it's a hallucination, but...
Yeah, I mean, no, not that kind of hallucination, but yes.
We have a couple people over here who've been raising their hands.
Hi, so I have a question regarding, I'm a neuroscientist, that most of our current understanding of brain function relies on pretty standard neurochemical, neurophysiological, and neuroimaging studies. So it's a bit, I think, not clear to me exactly why we need these quantum oscillations. When so much is really understood about how the brain functions, why do quantum oscillations, why are they so necessary from your standpoint?
I don't want to hog the mic here, but I disagree that neuroscience is really telling us a lot about how the brain works. We can't explain consciousness. We can't really explain memory. We can't explain free will and causal action. We can't...
So quantum oscillations can explain free will and self-awareness?
Yes, I think so. A collapse can explain awareness. As far as free will, there's a number. free will requires causality, causal action, and collapse of the wave function is the best way to do that. Also, the problem with free will, it involves the consciousness appears to come too late. You say something and I answer you. If you looked in my brain for the activity processing what you said, I will have already responded to you, believing that it's conscious. So neuroscience says that my action is on autopilot, is subconscious, and I have a false illusion, a hallucination that I was in conscious control. And I don't think that's right, because every collapse also has backward time effects. And Roger Penrose wrote about this based on Libet's experiments in 1979, which neuroscience cannot explain without quantum backward time referral. And if you have the backward time referral, then I am answering you consciously, because the processes are, the neural activity results are coming to me from the near future. As bizarre as that seems, there's very good evidence for it.
My other point about the oscillation is, to my knowledge, but perhaps you know more, there's actually no solid evidence for it. There's not much solid evidence for this oscillation idea.
Wrong. Sorry, you're just wrong. There's a lot.
There is a lot?
Yeah, we can measure megahertz coming from the brain right now, okay?
Which implies?
Well, that's not coming from neurons, it's coming from microtubules, and it's at the quantum realm. And it's functional. It correlates better with consciousness than does any EEG.
Okay.
EEG is obsolete. It just doesn't know it yet.
I can't argue further on that, but I'll ask you one other question on your aromatic, your emphasis on aromatic molecules. They can neither encode information nor catalyze information. So for me, the idea of the RNA world being more important in the origin of life makes more sense, because it could be that aromatic molecules contribute, but without encoding information and without enzymatic properties, how could they be involved in the origin of life?
First of all, RNA is aromatic. And it came along probably after aromatic rings, which were floating in the universe. So I mean, most people, 99.9% of the world is going to say, yeah, life came first. But how did life get from molecules to simple organisms with behavior without any motivation? Now, I hear all these, I had a debate with an evolutionary biologist, and she said, well, you don't need genes, all you need is reproduction. And I said, well, reproduction, last time I checked, feels good. So that's what's driving that behavior.
Okay.
We are co-authors. I thought the very first question that came up, but Richard kind of didn't bring up, maybe it's addressed to Nassim. To have consciousness, I guess we need to have sensation. And when the sensation, how do we sense? So we're talking about stimuli. I guess Richard could have mentioned the work of Donald Hebb in 1949, and then confirmed, in the last 70 years. So synaptic plasticity, it seems to us more basic than the microtubule that is inside the neuron, because we're talking about synapses. So we're really curious, how come this doesn't really come up very much?
Let me just say quickly, synapses are completely dependent on, their formations and maintenance is completely dependent on microtubules. Both forming the synapse, forming the neuron, transporting molecules by motor proteins for synaptic plasticity, and in fact the tau protein, which falls off and is associated with Alzheimer's, is actually a traffic signal telling the motor proteins to get off for synaptic plasticity. Synaptic plasticity is extremely dependent on microtubules.
I'm really puzzled now, because per neuron, humans have thousands of synapses per neuron. A C. elegans has hundreds of synapses per neuron. Why are you talking about neuron doesn't...
How many does a paramecium have?
Oh, is it?
How many synapses does a paramecium have, which can swim around, find food, find a mate, have sex?
It doesn't have a nervous system.
That's the point.
That's the point.
It has microtubules. The microtubules are the nervous system within each cell, including every neuron in your brain and your glia.
That has 3 chemicals before nervous system. It's not even neurochemicals.
Think of an antenna.
It's not chemical, it's quantum. Anesthesia is not a chemical reaction, it's a quantum interaction, makes no chemical reaction. That tells us the consciousness is not a chemical system.
Okay, thank you.
I feel so bad because this is another question for Stuart, but anyone can answer it probably. Given Froelich coherence and superradiance, does your famous equation that T equals h bar over E sub g, does that impose an upper bound on spatially extended coherence in the brain? Is there like a maximum spatial coherence?
No, you can have larger and larger E sub g. So there's about, in reference to this gentleman, there's about 1 billion tubulins per neuron. And there's, 10 to the 11th neurons, and then there's 10 times more glia, which also have microtubules, so we don't have to waste the glia. So if E sub g increases, you get more and more conscious, and time gets shorter, so it gets faster. So it's like a spectrum. So it's like photons. You can have very high energy photons or very low energy photons. So if you're meditating or if you're on psychedelics, you're at a very, very high rate, large E sub g, using more of your tubulins and your microtubules. Even though the energy requirement might go down, because like in the Carter-Harris experiment with IV psilocybin in patients with their eyes closed, their fMRI was cold and dark and their EEG was flat, yet they were hallucinating and actively conscious, but they weren't doing any cognition. So cognition requires energy. Consciousness is a very low energy process.
Thank you very much. When you hear all of this, you can see there is a lot of intelligence in the universe to create all this and to create all the people speaking here. Is this intelligence, before all this structure was created, is created with intention, and do you think there is an intention in all this universe, and part of the intention is evolution? This is my question to you, to all of you. Thank you.
Somebody else want to answer? I would say yes, but let somebody else answer.
Yeah.
They got it. Oh.
Thank you.
You go ahead. No, you go ahead.
Okay, I think I just want to say for the gentleman before, thinking of the brain without quantum dynamics involved, and thinking you're going to resolve consciousness is like a astrophysicist looking at a galaxy, refusing to acknowledge that stars are present in it. And so, you know, it's a scale problem. And a scale problem is vastly evident in quantum mechanics and classical physics. That problem is due to our compartmentalization of fields and the way fields interact to produce, you know, classical effects from the quantum state. So I just want to make that clear. You don't have the energy density at all at the brain level to produce what we call, you know, self-awareness. Second, I think that, you know, the question is fundamental to this idea that there was a bang, right? And so, I'm quite opposed to this idea. I'm quite opposed to not that there wasn't a bang, but the idea that that there is no cyclic relationship, and that we must identify something fundamental as something that is not in a relationship with something else, meaning that like somehow it existed. Well, then if you do that, you've started a new religion. You might have called it God, you might, you know, and I'm not interested, right? So you can have infinite cycles of information transfer in feedback information complexities that go from infinitely big to infinitely small. And it's just because we have this idea of a start and a beginning, which we don't actually see very well. Like, for instance, we don't see any proton decay, right? That doesn't really happen. And we consider that somehow this oscillator is just magically oscillating in space, right? Which is the same problem. So I don't know if I'm answering your question, but I'm saying think of cycles, think of relationships, continuous relationship which produce evolutionary system, fractal scaling, and that produces the complexity of a human being. I was having fun the other day calculating the number of protons in a human being, and it exceeds the number of stars in the universe. So complexity is high.
If I ask the question another way, is a consciousness not as human, but consciousness can be beyond the human, on the other level? Consciousness of all the universe together is conscious, and we are part of it in the same way cell is part of it. We are consciousness is part of much bigger consciousness, and there can be any other hierarchy of consciousness.
Right. The tendency is to make these separation. That's what I was trying to bring to you. Is the idea is that there is feedback mechanism between the electromagnetic field and the gravitational field at all the scales. And these are bleeding from one scale to the other. This is like the coupling constant I was showing. And the result is that the system can become very complex and show this behavior, these same dynamics of self-awareness at another scale that we experience every day and we call our consciousness. But that this information feedback loop is just like a thread across all scales.
Can I ask a question to
I don't
Suzanne?
know if it helped.
I think I have the mic.
I got one too.
Yeah. So I really liked your answer to the question about there must be new physics in the quantum collapse and then classical loop. And but to take a little bit further, do you agree with Penrose that in the collapse, it's not computational, not deterministic, and not random?
Yes, I do, although it depends on your definitions. So kind of what I think is that like the universe, everything participates in the computation of that collapse happening. So it is something that gets computed, but it gets computed by a computer that is so vast and huge compared to the kind of things we do today that it sort of looks non-computational, it looks indeterministic from our point of view. So I guess that's kind of a definitional problem. But if you think of the entire universe as a computer, maybe that looks uncomputable to us. So that's kind of what I think is computing the collapse.
Okay, thank you.
Yeah.
Hi, I'm Sarah from Radio Fribourg, Switzerland. I don't have a scientific background, so sometimes it's hard to grasp all the details and explanations. So are you able, all of you guys, to say, okay, this theory is right on this point and this contains errors? So are you able to say which, or do you agree on each other? And what is wrong to each other's theories? Like, we all want to know.
I don't think we have time.
Yeah, we don't, but are we able to do something like, what do you agree on as, or what is really wrong about you?
I'll try and start. I think we're all talking kind of about the same thing. But I think like this whole space-time, it's oscillating. Everything's oscillating. There's nothing that doesn't oscillate. Even information. Information, if you're reading it on a piece of paper, it's oscillating. Even you thinking is oscillating. The periodic table of elements, it's all oscillating. There's nothing that you can point to that doesn't oscillate. So remember that. But I think we're all talking about the same thing. I think space-time is oscillating, and I think we're kind of saying that a little bit, and we kind of think that space-time it's made up of little networks of something. I'm saying it's space-time crystals. But if that's true, that means we're all entangled with it. We're not just in space-time. We are all literally entangled with it. This whole entanglement thing, that's just because you have a particle here, it's entangled by little space-time crystals, and there's another particle over there, and they're at the right frequency, and that's why they're entangled. Why are things probabilistic? Because you have little particles having to navigate a whole sea of little nodes, little networks. They're trying to, move around, and everything's affecting everything. So that's why it's probabilistic. Our measurements are literally saying that, in my mind. And I think we're all saying the same thing, just coming at it from a different, perspective.
I think on that, I think we all agree with a fundamental premise that there is a fundamental field from which all these effects are emerging, and that field is a nonlinear field which has very fundamental, like maybe Wheeler type of wormhole interaction that makes the complexity very, very high, and that produces a probabilistic equation in the standard model of quantum mechanics, but that probabilistic equation is actually not ontological, meaning that it's only probabilistic. The Heisenberg uncertainty principle is only there because we have an uncertainty because of our capacity to compute the data, but that the universe is not ontologically confused about the position and the momentum of a particle. And that really is a very important distinction. And I think we're all kind of making this distinction in various ways. On that, I want to mention just technically that the Heisenberg uncertainty principle actually emerged naturally from quantum vacuum fluctuation, not the other way around, and that's very much confused in the literature. That is, like, the literature continuously teach students that zero-point energy fluctuation or quantum vacuum fluctuation comes from Heisenberg uncertainty. It's completely confused. Zero-point energy quantum vacuum fluctuation comes from equations from black body, from Max Planck solving black body equations that showed that at 0 Kelvin there's still oscillation in the structure of space.
So if you agree there are impacts in science?
I'm sorry?
If you agree there are big impacts in
Yes,
science?
I think we're on the very edge of bleeding science in very big impact capacity. And you will find different views of the same thing from everybody because we all look at the universe a little bit differently, and that's why we're all actually in the feedback loop looking a little bit differently from one another. But I think that we're arriving at a very important part, and it has huge implication for technology as well. And that's one thing I like to talk about as well, is that there's huge implication for energy production, for gravity control, for technological application to life extension and all kinds of things that will completely transform our world. De rien.
Sorry. I have two questions. First question is to the lady. And you mentioned about the quantum consciousness, right? And you want to use quantum consciousness on the machine, right? So I also focus on the topic of quantum consciousness. But someone will argue, they said that since the machine's brain is not a biological structure, but our human brain is biological structure. So our human brain has the microtubulus, but the AI machine, the brain, didn't have the microtubulus. But how did you make the quantum consciousness happens in the AI's brain? This is the first question. And the second question is to Dr. Hameroff. And you mentioned about the collapse happens in the human brain, the microtubulus. The OR causes the consciousness. Do you think that the collapse in the microtubulus will also cause the free will? This is my question to Dr. Hameroff. Thank you. Thank you.
Yeah, I can answer the first question. So, I mean, like, as Stuart's presentation showed that the quantum state is orchestrated by the microtubules, but what I'm saying is that it's still a quantum state underneath. So, could we use the quantum computers we have today to create a quantum state independently of microtubules? And if it's the quantum state itself, if it's something deeper, like people have been saying here, if it's a property of quantum fields or quantum systems more generally, then you can have consciousness in substrates other than biological. But it is yet to be tested as to whether there can be a consciousness in a system other than a biological substrate. But if everyone believes that it's just quantum theory and quantum mechanics that causes the consciousness, then there's no reason why it has to be biological. It could be any quantum system. Maybe you need it hooked up in the right way in a feedback loop with the environment, but any quantum system should be able to have this property of consciousness.
So without the microtubules in the machine's brain, there will also quantum consciousness, right?
Yeah, there are other types of structures that are non-biological, but they made from superconductors or photonics or trapped ions. They're all quantum systems that you can test. Yeah.
Yeah,
free will. You're Owen, right? Yeah. I wrote a paper, How Quantum Brain Biology Can Rescue Conscious Free Will, which in 2012 in Frontiers. It's my most popular paper, and I recommend you read that. But I have to say one thing. To the neuroscientist, the gentleman who was claiming that we don't need microtubules because neuroscience can explain everything, and I rattle off about 10 things, thank you, that it doesn't. The most important, Alzheimer's. Neuroscience sucks in Alzheimer's. There's two lesions, amyloid plaques and neurofibrillary tangles. And for 35 years, neuroscience and big pharma and everybody else has been attacking the amyloid plaques. Doesn't do a damn thing. They're toxic, expensive, they're making a ton of money and not doing anything for patients. The lesions, the microtubules fall apart, the tau falls off the microtubules, forms these neurofibrillary tangles, which are a sign of Alzheimer's. But the tau isn't toxic. It's the fact that the microtubules fall apart. You lose synapses, you lose neurons, you lose brain volume. Okay, so what do you do about it? No drug's going to fix it, but you can resonate the microtubules because they have megahertz with ultrasound. And there are many, many studies. There's about a couple dozen studies now showing marked improvement in Alzheimer's symptoms, including reversal of cortical atrophy, where the brain is actually shrunk and it grows back along with memory improving markedly because apparently we're resonating the microtubules to repolymerize, reestablish synapses, and regrow the brain. So that's what we should be worried about. Forget the damn amyloid, please.
Thank you. Before furthering any comment, I wanted to thank you all. It was utterly elucidating. Seeing people with different background. I'm coming also, like Sarah, from a different universe, parachuted into a consciousness. So it's fascinating to see how all of you acknowledge that there is a part computable and a part non-computable, which I would that itself addressed with the Nobel Prize. Last one being given to a certain Daniel Kahneman for economics. So he was predicting how the models and how the consciousness of the market make people rich or less than rich. And he's a psychologist. So was coming from a different field. You all are mixing fields and finding something which is utterly beautiful. So first of all, thank. And a comment is for the future research, echoing Sarah as well. Where would you put, if you have to invest 100 nickel or whatever grant EOMs would grab, where would you put your coin in? So what would be, we established, Nassim said that there is something there in the vacuum that has been called in the centuries, even from philosophers, ethers and other things. So now we prove it. Stuart said, and Penrose, there must be something there, yes, to be disproved. So it must work like in all theories, in any field. What is the next point to take from here to something that benefits the whole of humanity, to make it something that is public health versus health?
Treat Alzheimer's with a $150 machine that you can hold in your hand. Every patient in a nursing home can get 100 treatments, 100 patients a day you can treat for $150 instead of $40,000 a patient for a toxic anti-amyloid drug that doesn't work.
Agree that my universe was the World Health Organization, so you can imagine how in agreement I am.
Well, why don't you get the World Health Organization to get on the stick about Alzheimer's and forget the damn amyloid and treat the microtubule falling apart?
Because I got fired and been substituted by a military American doctor. Yeah. Because they didn't agree with my position. But this is a separate conversation. Now, seriously, not just health, but the wars and so on. What you are discussing here has a big dividend for a larger conversation, and I want to have a comment on that level, how you move it to the next level. Thank you. Really, thank you.
I
do
could
thank
suggest one thing. Maybe take half of it, and I think you need more like 500 million. Maybe take half of it and endow like 50 endowed chairs in academia across the country for this research, because they're still so prominent in the scientific community, the view that quantum mechanics has nothing to do with consciousness, and that consciousness has nothing to do with physical reality. And so we need many people supported to actually do this research as a career, and then also particular focused efforts like Alzheimer's and conscious robotics and that kind of thing.
Where to put your money in the research was one of the hottest debates at the MIT in those days.
We have a project with IONS, with Thomas's organization, to do studies with a very inexpensive ultrasound device to treat. This is so cheap. You know, we could do the whole study for what one patient pays for the damn drugs that don't work per year. So that's where the money should go. And it doesn't need a lot of money. That's why nobody wants to do it, because big pharma can't make any money. Big neuro can't make any money out of it, because it's a bottom-up type of thing.
I have one thing to say. If you had to put money in something, I think quantum computation will go away. I don't think it's about bits. I think that's just how you put a straitjacket on computation. If you really want to do real computation, look at phase dynamics. Just phase dynamics. That'll do the real computation. Really.
Can I argue something with that? So,
Sure.
I don't think quantum computing should go away. I think we should try and apply it to more interesting use cases that are a bit more outside the box. So, you know, if quantum consciousness is a hypothesis that's taken seriously, and we can apply quantum computers to it to learn more about it. People are using quantum computers to just try and do the same old math faster, trying to break cryptography, I think that's boring. Like, let's apply them. Let's think of new things, new algorithms. Let's see how far we
I guess what I'm saying is just that I think what we're really describing is phase dynamics. In every single.
Quantum computers have phase dynamics.
No, but quantum is phase. Remember what I'm saying. When we're doing quantum computation, we're just doing phase dynamics with straitjacket. Just. Yes. It's the same thing, but better.
Maybe linear computers could help.
Tell me which computer could predict Assad demise in a week after 40 years of regime.
Just.
No intelligence. Now I'm done my part.
You can solve quantum algorithms using a regular classical computer with a Python program focused on phase dynamics. Yeah, that's going to be a thing. Trust me. Yeah.
Hello, thank you so much. I have one question to Suzanne and another question to everyone. So your presentation reminded me of an idea of Daniel Dennett, who distinguishes between the mechanistic stance and intentional stance. And so, like, I have very limited knowledge about LLMs or like AI systems, but when you're coming up with an output, when a system comes up with an output, it chooses randomly between equal weighted options, basically. But It's actually just a random process, like the mechanistic stance is just a random physical process, but the intentional stance is what we attribute when we say the system chooses randomly. So, but I get that in your framework, the system literally chooses. So, like, can you delve deeper into what makes this choice, what distinguishes from a random physical process?
Mm-hmm. Yeah, that's a good question. So in the framework I work with, this, as I mentioned before in response to the other question, quantum mechanics, when we test very small, like isolated quantum systems, it appears to be random. And by random, it selects like from a probability distribution, which is shaped by the Schrödinger equation. But then when it collapses, it appears to sample randomly from that probability distribution. But that's only in the quantum systems we've explored so far. So what I'm looking at is, are there quantum systems where that rule breaks and you don't see this random sampling anymore? You see what you might call more of an intentional process, which comes from what I think is, I call it the universal reward function, but it's like a process whereby a wider quantum system or a quantum field that everything is entangled with actually makes an intentional choice. And what is it choosing to do? It's choosing actions that will help it maximize future conscious experience and well-being. So this actually ties in quite nicely to one of the earlier questions about evolution. So in this framework, evolution is kind of a byproduct of consciousness trying to emerge and expand and have more experiences. So if you're an idealist, everything is consciousness. And what happens is consciousness makes actions at the very small scale, even like the atomic or electron level, to try and pool more of itself together to have richer and richer experiences. And eventually that builds up to things like organisms that then start reproducing. But that like drive is baked in at a much deeper level of the universe. So you have to ask the question, if you're a kind of a Darwinist person that believes in like natural selection alone, why didn't it stop at bacteria? Because bacteria are much more successful in evolutionary terms than we are. They're much better adapted to the environment, but somehow evolution wants to make bigger and bigger and bigger brains. And so maybe it's not just maximizing survival of the fittest, but it's actually maximizing the most conscious experience. And that would then be compatible with the evolution because reproduction makes more conscious beings. But there's this like thing on top of it that also tries to maximize consciousness. So that's kind of what I think about that. Is there an intentional purpose? Is there a purpose to the universe? Yes, absolutely. And it's not just me saying this. People have said this throughout the whole of history, including physicists like Bohm with the implicate order, Platonic value systems, all these kind of things. So it points to this same idea that the universe has a kind of blueprint and it's making choices through this kind of quantum uncertainty loophole that steers it towards more consciousness in the future.
Yeah, I think we could say ontologically, Dennett's view was that consciousness is an illusion, just a misinterpretation of the randomness. But this view is that consciousness is real, and the randomness of the Born rule is a illusion.
Yeah, thank you so much for the answer. And the other question is that when, Stuart, you were answering a question, you said that, for example, we cannot explain why green feels like green and not red. But I think it's one of the main motivations of David Chalmers, where he says that he's a dualist because even though we locate consciousness at the most fundamental level of the universe, we are still, we're just in the explanation level, but not in the qualia or like the phenomenological experience level. So the question for all of you is that, do you think your frameworks can explain this question of why red feels like red or why green feels like green? And do you think this question is as important as explaining where consciousness comes from?
I could answer it. I think I'm mic'd up. So I have a paper out that's called Unified Physics in the Entanglement Nexus of Awareness. And that's actually the main subject of the paper, is addressing the objective-subjective dichotomy that is generated by a conventional scientific purview of what is the nature of consciousness, particularly consciousness as an epiphenomenological state. And so this also ties in somewhat to the previous question on we're all presenting different ideas. Is there any areas of contention or disagreement? I wouldn't say that, but like one of the things that I was presenting was an extension of the ORCH-OR theory. So it's not really a critique of it, but more just how can we extend it to more and more phenomenology and a generalization of the ORCH-OR theory. And one of the things that I was highlighting was the involvement of entanglement and the equivalence of quantum entanglement with space-time topology. And so in my paper on the unified physics and the entanglement nexus of awareness, one of the things that I point out is that if we have these quantum states in the brain that are driving brain biology that is correlated with conscious experience, those states involve things like entanglement. And so when we're perceiving qualia, like the redness of a rose, we're actually entangled with that quantum system that's in the environment. And so our experience of that quantum system in the biological domain of our brain is being shaped by input not only via like the visual senses, but the quantum state of that system and the information transmission that's occurring non-locally.
I understand that.
Yeah.
But even though there is this entanglement with the rods, why does it feel like red but not green? So how does the information correlate with the qualia we have?
Yeah, great question. Because that information exchange is occurring with the entire space memory network.
That's right.
You know, so somebody who is experiencing the quantum state and the corresponding qualia of that rose, they're actually feeding that information back into the system. So actually, their qualitative experience of that system is shaping its behavior and shaping its property. So this is where we resolve the subjective-objective dichotomy, where objective materiality, so to in the conventional purview, is what is real and what has an effect, but subjective experience, or qualia, has no reciprocal effect on the objective domain. That's where we resolve that, is that, well, actually, we're feeding information back into the material domain, so to speak, and so actually our subjective experience is affecting the so-called objective material world. And so if we're experiencing red, we're feeding that information back in. Anybody else experiencing the quantum state of that flower, they're receiving the information that we're feeding back in, and they're going to experience red. And you kind of build up a consensus among all receivers.
Objective is subjective.
Objective is subjective.
So we're at time, and the stomach has consciousness too. We don't want to miss the reception snacks. Maybe we should take one quick answer to this good question from each of us as the final.
I'll address that. You know, that's a key question about you see red, I see blue. And I think the answer is in the, you know, it's encoded somehow in space-time geometry. First of all, we know that the tubulin, just by its van der Waals oscillations, generates blue-green light, 489 nanometers, under normal circumstances. So maybe it shifts and it's a different color. But I think the answer is that it's encoded in the space-time geometry. They have different, Nassim and William and Nestor have maybe different descriptions of it. I just showed it as different curvatures as a cartoon. But the qualia are fundamental and should be embedded in the basic level of the universe, and then we entangle with that, and that's why we experience red. And as for Dave, he's a good friend of mine, but he's a philosopher, and he's been on every side of every argument, so it's hard to pin him down on anything.
I guess I would answer this question. Like, I don't really know, but from the framework I'm working with, this quantum conscious agent theory, you have like a quantum state, and then it has an interior, which is like the quantum wave function, and then it has an exterior boundary bits around it, which are classical. So it's a bit like Donald Hoffman's conscious agent networks, where these things exchange information with each other. So you could ask, well, if the same information classically is coming in through the boundary, and then the agent is very very similar, then I would expect the quantum state that emerges inside it will be similar. So the red will be like your red, but I don't know that for sure because none of us know. We can't actually look inside a quantum state. Once we make a measurement of it, we only see a projection of it, so we can never know the interior of that. But my suspicion is that they will be the same if the boundaries, so the input-output bits are similar.
Yeah, I think whenever we're making an observation, we're always influencing whatever we're looking at, even subtly. If we're looking at a painting, literally our field is interacting with the field of whatever we're looking at. And when it hits our eyes is demodulating that field. So I'm being altered by what I'm looking at. And because I'm making sense of it, I'm encoding it in my memory at the same time as I'm trying to make sense of it. Otherwise, I wouldn't be able to make sense of it. So there is this feedback. You're looking at me, I'm looking at you, you're encoding, I'm encoding. If we could measure it, there would be a change. So I think the subjectivity is the fact that I'm looking at you at a certain angle that no one else could see you right now. Even though she's right next to me, she can't see you. That's where the subjectivity is. It's in the space-time geometry, in the visual aspect. So I think that's kind of where subjectivity comes from, because everyone here could sit in my exact position and be looking at you, but they would look at you differently. One, because they can never see the perfect angle. But two, they see differently. They have different hardware. They have different experiences of what it is to see something. And I think that's where the visual subjectivity, but it's analogous to everything else. So yeah, I think that's where it comes from, the geometry.
Yeah, I think it's really important to go back to, is consciousness fundamental? If consciousness is fundamental, that means that, let me put it the other way. That would mean that there is fundamental mechanism that produces that self-awareness dynamic and the event of complexity in a system. And that requires, very specific physical dynamics that can be computed. However, these dynamics include infinities due to interactions in the field. And so it's never, the tendency we have is to identify, okay, we put a box, we isolate a system, and we say, okay, there's a rose there, and there's a person there, and why are they having this experience? And I think that's the wrong question to ask. The rose is in a field, and we're in a field that interacts with all things, at all levels, in all scales, and the relationship is more complex than a single relationship between a rose and a person. And it's the correlation of all of these events, all of these observations across the whole. This is how Wheeler ended up thinking, maybe there's just one electron going across the wormhole, across the whole universe. It's actually a network. It's a neural network made of wormholes, and then that eventually reaches complexity at our scale that makes up what we call, the brain antenna that brings us to self-awareness. So I don't know if I'm saying this correctly, but mathematically, there's actually rigorous mathematical ways that you can describe this dynamic, and it has nonlinear functions like a fractal, right? A fractal is simple equation that can give you infinite, complexity. You can have this type of dynamic where you can write the equation for it, but the output of the equation is not something you can compute.
I think it's Platonic domain, which can be generalized to metaphysical domain, and it's also feedback, subjective, objective feedback, and I think it's opening up a window into a domain of reality that science is we are just starting to bring into modern science in a modern way that will, like Nassim said earlier, potentially revolutionize a lot of science and technology.
Thank you.
Thanks, everybody.
I liked your talk the best.
I think we do have a reception out here, 6 to 7, don't we?